Hello there and welcome to Physics with William, where difficult ideas get a little more time than usual, complicated questions are allowed to unfold slowly, and mathematics is permitted to be strange without immediately becoming stressful. Tonight we're looking at one of the most controversial ideas ever added to modern mathematics. It is called the axiom of choice, and despite the rather serious reputation it has acquired, it begins with an action so ordinary that you probably performed it several times today without noticing. You chose something. Perhaps you chose what to eat for breakfast. You chose which shirt to wear, which message to answer first, which chair to sit in, or which tab on your browser to close after realizing you had somehow opened 14 of them. None of these decisions seems mathematically important. You had several possibilities, you selected one, and life continued. The axiom of choice begins with exactly this familiar act, but mathematics takes it into a situation where our ordinary intuition is no longer quite enough. Before we get there, I would love to know where you are listening from tonight. Are you somewhere quiet, perhaps already in bed, or are you listening while working, travelling, or attempting to convince yourself that learning about the foundations of mathematics counts as relaxation? And here is another question that fits our subject rather well. When you have several perfectly acceptable options in front of you, are you someone who chooses quickly, or do you compare everything until the decision becomes far more important than it ever needed to be? There is no correct answer, although anyone who has spent 20 minutes choosing something from a restaurant menu may suspect that choice itself deserves more scientific attention. If you enjoy these slow journeys through science and mathematics, you can leave a like and subscribe to the channel. It helps this quiet corner reach other curious people who enjoy learning something unusual without being rushed through it. And if you happen to fall asleep before we reach the stranger parts, mathematics will still be here tomorrow. It has waited several thousand years already, so another evening should not cause too much trouble. The axiom of choice can be introduced with a very simple situation. Imagine that I place several boxes on a table. Every box contains at least one object, and I ask you to take exactly one object from each box. Suppose there are 3 boxes. The first contains apples, the second contains pencils, and the third contains small wooden blocks. You choose 1 apple, 1 pencil, and 1 block. Nothing mysterious happens. You can see the options, make the selections, and finish the task. Now suppose there are 100 boxes. The job becomes more tedious, but it does not become conceptually strange. You start with 1 box, make a choice, move to the next, and continue until you have dealt with all of them. Even if there are 1,000,000 boxes, the practical problem would be enormous, but the logical idea remains clear. There is still a finite number of boxes. There is a first one, another after it, and eventually a final one. Given enough time, patience, and a truly unreasonable warehouse, the selections could in principle be completed. The situation changes when there are infinitely many boxes. Each box still contains at least 1 object. You still want to choose 1 object from each. The instruction has barely changed, yet we have crossed an important boundary. It is tempting to say that the answer is obvious. If each box contains something, just pick something from every box. That reaction is precisely what makes the axiom of choice so interesting. It sounds obvious because choosing from 1 box is easy. Choosing from 10 boxes is easy. Choosing from any finite number of boxes is easy in principle, so our minds naturally extend the same idea to infinitely many boxes and assume nothing important has changed. Mathematics asks us to be more careful. Suppose every box contains positive whole numbers. In that case, we can choose the smallest number from every box. We have a rule. It works for 1 box, 1,000 boxes, or infinitely many boxes. We do not need to make a separate decision every time because the instruction tells us exactly what the chosen object should be. Choose the smallest number. That is enough. Now suppose every box contains 2 shoes, 1 left shoe and 1 right shoe. Again, there is a simple rule. Choose the left shoe from every box. There might be infinitely many pairs, but the selection itself is easy to describe. We know exactly what distinguishes the chosen object in every case. Now replace the shoes with pairs of completely identical socks. Each box contains 2 socks. Neither is labelled, neither is smaller, neither is brighter. There is no left sock and right sock in the same useful sense that there is a left shoe and a right shoe. For an individual box, you can simply reach in and take one. But we are not dealing with one box. We're considering an entire infinite collection. What rule tells you which sock to choose from every pair? You might say that you would simply take whichever sock your hand touches first. That would work if you were physically standing in front of one box. But mathematics is not asking for a physical story about your hand. It is asking whether there exists a complete selection containing exactly one sock from every pair, even when there is no rule describing which sock should be selected. That is the important step. The axiom of choice says that the selection exists. If you have a collection of sets, and none of those sets is empty, then you may choose one element from each set, even if the collection is infinite, and even if no explicit method tells you how to make all the selections. This is where something that sounded like common sense starts becoming a serious foundational statement. The axiom does not tell you what the selected objects are. It does not give you a procedure for finding them. It does not provide a machine that can produce the choices. It does not promise that there is some clever pattern you simply have not discovered yet. It says only that the complete selection exists. To understand why anyone would object to that, it helps to think about what mathematicians mean when they say that something exists. In everyday life, existence usually feels straightforward. If I tell you that there is a mug in the kitchen, you can walk into the kitchen and look for it. If I claim there is a book on a particular shelf, I can point to it. If I tell you there is one biscuit remaining in the cupboard, there is a reasonable possibility that this statement can be tested almost immediately. Mathematical objects are different. You cannot place an infinite set on a table. You cannot walk around a function. You cannot open a cupboard and discover an abstract space sitting behind the cereal. Mathematicians therefore rely on proof. Sometimes a proof gives you an explicit object. It shows you exactly what to construct and how to construct it. At other times, a proof can show that an object must exist without actually presenting the object itself. This second kind of argument is called non-constructive reasoning, and it has a long and important place in mathematics. Imagine, for example, that you can prove logically that at least one person in a large crowd has a certain property, but your argument does not identify the person. You have established existence without finding the example. Many mathematicians are perfectly comfortable with this. But the axiom of choice pushes the idea much farther, because it allows existence to be asserted across completely arbitrary infinite collections. Suppose there are infinitely many non-empty sets. Some may be easy to understand. Others may contain objects so complicated that we cannot visualize them at all. There might be no natural ordering, no smallest member, no first object, no label, and no procedure that picks one consistently. The axiom says that none of this prevents a complete choice from existing. To supporters, this is a useful and natural principle. To critics, especially when the axiom first became an important topic in the early 20th century, it looked like mathematics was claiming the result of an infinite number of decisions without explaining how even one general method could make those decisions. The disagreement became much more than an argument about boxes and socks. It touched a deeper question. Should mathematics allow us to claim that an object exists when we cannot construct it? Different mathematicians had different instincts. Some believe that mathematical objects could exist independently of our ability to describe them. If logic showed that an object must be there, that was enough. We might never find it explicitly, but our ignorance would not remove its existence. Others were much less comfortable with this approach. They wanted mathematical existence to remain closely connected to construction. If someone claimed that an object existed, they wanted a process that could, at least in principle, produce it. The axiom of choice sat directly between these two attitudes. There is a useful way of seeing why the problem does not arise with finite collections. Imagine 5 boxes, each containing at least one object. You can choose from the first box, then you choose from the second, then the third, fourth, and fifth. You have finished. No additional principle is required. The same works for any finite number of boxes. The procedure may become absurdly long, but it always has a last step. With infinitely many boxes, there is no final box where you can put down your pencil and announce that the selections are complete. Of course, mathematicians can describe infinite objects without performing infinitely many physical steps. An infinite sequence is treated as a complete mathematical object. We do not require someone to spend eternity writing its entries. But an infinite sequence usually has some rule defining what appears in each position. The axiom of choice becomes important when that kind of rule is missing. Imagine an enormous library containing collections of books. You want one representative book from every collection. In one section, perhaps every book has a number, and you can choose the book with the lowest number. In another, perhaps titles can be arranged alphabetically, so you choose the first one alphabetically. Those collections do not create much difficulty because there is a selection rule. Now imagine collections whose members have no useful labels and no natural order. There is nothing about one member that marks it as the preferred choice. The axiom of choice allows you to say that a representative can still be selected from each collection. You do not need to know which representative. You only need to know that one exists. This sounds like a small technical convenience, but it has enormous consequences because mathematics constantly deals with collections where selecting representatives is useful. Suppose many objects are grouped together because mathematics regards certain ones as equivalent in some particular way. A mathematician may want to choose one representative from every group. If there are only a few groups, that is straightforward. If there are infinitely many groups and no natural representative inside each one, the choice becomes much less obvious. The axiom solves the problem immediately. One representative from each group exists. The proof can continue. This ability turned out to be extremely powerful. Entire mathematical arguments become shorter and cleaner when choice is available. Important results across several fields rely on it directly, or rely on other principles that turn out to have exactly the same logical strength. That last point is especially interesting. The axiom of choice has several mathematical relatives that look very different on the surface. Some talk about ordering sets. Others talk about finding maximal objects inside certain structures. Others concern the existence of bases in large mathematical spaces. At first, these statements appear to be unrelated. Then mathematicians discovered that some of them are equivalent. If you assume the axiom of choice, you can prove these other statements. If you assume one of those statements, you can recover the axiom of choice. So a mathematician can avoid saying the words axiom of choice and still use something that amounts to exactly the same assumption. It is a little like avoiding sugar while eating a dessert whose ingredient list has simply become more creative. This equivalence helped make the axiom deeply embedded in modern mathematics. It was no longer one odd statement about picking objects from sets. It was connected to many powerful theorems that mathematicians genuinely wanted to use, yet usefulness did not remove the discomfort. One reason was that infinity was already causing trouble elsewhere. During the 19th century, mathematicians began studying infinite sets with a level of precision that had never existed before. They discovered that infinity was not one simple size. Some infinite collections can be matched exactly with the positive whole numbers. They may contain endlessly many elements, but they can still be placed into a sequence. Other infinite collections are larger. They cannot be listed in that way. This was a profound shift in how mathematics understood infinity. Our ordinary language gives us one word, infinity, and encourages us to imagine something that simply never ends. Modern set theory revealed a much richer landscape. Once these different infinite collections entered mathematics, statements involving words such as every, all, select and arrange became more delicate. A collection might be infinite without having the sort of simple order we instinctively imagine. When someone says choose from the first set, then the second, then the third, we should immediately ask whether the sets can actually be placed into such a list. Sometimes they can. Sometimes that is exactly what still needs to be proved. This is why the casual phrase "just choose one from each" can hide so much difficulty. Our minds supply an invisible procedure because we picture a manageable sequence of choices. Mathematics is not allowed to assume that convenient sequence unless it has been justified. The axiom of choice bypasses the need for such a procedure. It says that regardless of how complicated the collection is, if every set contains at least one object, a simultaneous selection exists. That word simultaneous is helpful here because it prevents us from imagining an immortal person carrying out choices forever. The axiom is not describing a process happening in time. It treats the completed selection as a mathematical object. There is one selected element associated with every set. The entire thing is considered at once. For some mathematicians, this was completely reasonable. For others, it sounded dangerously close to saying, "We cannot tell you what this object is, we cannot tell you how to build it, and we may not even be able to describe its individual pieces, but please continue under the assumption that it is definitely there." You can see why the discussion became lively. Then the situation became stranger because the axiom began producing results that seemed to violate ordinary geometric intuition. The most famous of these would eventually show that a mathematical sphere can be separated into a small number of extremely unusual sets of points and rearranged to produce two spheres, each identical in size to the original. No extra material is added. The sphere is not stretched. One becomes two. This is the Banach-Tarski paradox, and we will come to it carefully because the statement sounds far more physically impossible than the mathematics actually claims. For now, what matters is that such results made the philosophical debate impossible to ignore. If accepting a seemingly harmless rule about choosing elements could lead to a sphere apparently duplicating itself, perhaps the harmless rule deserved a closer look. But rejecting the axiom came with its own cost. Without it, many useful theorems could no longer be proved in their usual general form. Mathematical structures that were guaranteed to exist under the axiom might no longer be available. Arguments that had become standard would need additional assumptions or completely different approaches. Mathematicians therefore faced a genuine trade-off. Accepting the axiom gave them a powerful mathematical world filled with elegant results, but also with objects and constructions that could be extremely counterintuitive. Rejecting it avoided some of those strange consequences, but it also removed tools that had become valuable throughout mathematics. There was an even deeper question hiding underneath all of this. Could the axiom itself be proved? If it were simply a consequence of more basic principles, the controversy might eventually disappear. Mathematicians could show that choice was not really an optional assumption at all. It would follow logically from foundations everyone already accepted, or perhaps the opposite would happen. Maybe someone would prove that the axiom produced a contradiction, and the entire matter would be settled by rejection. Neither happened. The 20th century eventually brought one of the most remarkable answers possible. Under the standard framework of set theory, assuming that framework itself is consistent, the axiom of choice cannot be proved from the remaining usual axioms. It also cannot be disproved from them. Mathematics leaves room for both possibilities. You can study a mathematical universe in which the axiom of choice is accepted, and you can study one in which it is not. Both can obey the underlying rules consistently, again assuming those underlying rules are themselves consistent. This makes the axiom especially unusual. It is not merely a difficult theorem whose proof no one has found. It is independent of the other standard assumptions. If you want it, you add it. If you do not want it, you can investigate what mathematics looks like without it. The axiom of choice is therefore, quite appropriately, something mathematics itself asks you to choose. Today, most mathematicians working in many mainstream fields are comfortable accepting it. Often it is used so routinely that no philosophical discussion is required. A proof may invoke a result that depends on choice, and everyone simply continues. But knowing the history changes the way the axiom looks. Behind that small statement is a disagreement about infinity, existence, construction, logic, and what mathematical proof is allowed to give us. And its real power becomes clearer when we stop thinking about ordinary boxes. The examples with apples, shoes, and socks are useful because they make the basic problem understandable, but they are still far too friendly. In serious mathematics, the collections involved can be enormous, the objects can be impossible to visualize, and there may be no natural procedure for selecting anything at all. That is when choosing one object stops being an everyday action and becomes a foundational problem. To see why, we need to look more closely at the moment when simple selection fails, when there is no obvious first object, no natural ordering, no label to follow, and no process that can quietly do the work for us. Once all of those conveniences are removed, the sentence "choose one from each set" begins to mean something very different. The comfortable examples disappear surprisingly quickly once mathematics removes the little conveniences that make ordinary decisions easy. In daily life, when we say that we can choose something, we usually have far more information than we realize. Objects have shapes, colors, positions, names, sizes, labels, histories, and all sorts of accidental features that allow us to distinguish one from another. If two mugs are sitting on a table, you can choose the one on the left. If two books are stacked together, you can take the one on top. If two apples look identical, you can still reach toward one of them because they occupy different places. Our physical world constantly supplies hidden selection rules. Mathematics can take all of those rules away. Imagine that instead of physical objects on a table, you are dealing with collections described only by their mathematical properties. There is no left side, no nearest object, no brighter colour, no first item you happen to notice. You know that every collection contains something, but that may be almost everything you know about it. You're then asked to select one object from each collection. The request sounds familiar, yet all the ordinary tools that make choosing possible have quietly vanished. This is where the word arbitrary becomes important. An arbitrary collection is not required to be friendly. You cannot assume that its objects arrive in an order you recognize. You cannot assume that one of them is smallest. You cannot assume they have names. You cannot assume that there is a simple rule that separates one member from the others. Mathematics is asking whether a selection can exist even when the collections offer you no obvious guidance at all. Suppose we begin with a very orderly example. Imagine many collections of ordinary positive whole numbers. From every collection, choose the smallest number. The task may involve infinitely many collections, but the rule itself is simple. You do not have to make each choice personally. Once the instruction is given, the selected object in every collection is determined. Now imagine collections of words written in an ordinary alphabet. If every collection has a first word according to some agreed ordering, you can choose that one. Again, a rule does the work. The interesting cases begin when there is no such rule. Consider a collection containing two objects that are mathematically indistinguishable, except for being different objects. You know there are two of them, but nothing in the description gives one a preferred status. If you are dealing with a single collection, that does not feel troublesome. You can simply say, choose either one. If you're dealing with 10 such collections, you can still imagine making 10 decisions. If you're dealing with 1,000, the same principle works, even if your patience does not. With infinitely many collections, however, the phrase choose either one begins to hide something. What exactly determines the complete result? For any individual collection, there is no difficulty. At least one object is present, so at least one selection is possible. But the fact that each local decision can be made does not automatically give you a single global rule describing all the decisions together. The axiom of choice is what allows mathematics to cross that gap. This distinction between local possibility and global selection is easy to miss because finite situations train us to ignore it. If I hand you 20 envelopes and tell you that each contains at least one card, you can open them one at a time and keep one card from each. You do not need a grand theory of selection. You simply finish the job. There is a final envelope. Infinity removes that last step. And even more importantly, some infinite collections cannot be arranged in the simple order our imagination keeps trying to impose on them. We naturally picture a first set, then a second, then a third, and so on. But that picture already assumes something about the structure of the collection. It assumes that the sets can be listed in a sequence. Not every infinite collection comes with such a list. This is one of those moments when ordinary language becomes slightly misleading. When people hear infinitely many objects, they often imagine something like the counting numbers, one, then another, continuing without end. That is one kind of infinity, but it is not the only kind. There are infinite collections that cannot be captured by a simple, endless list. They are larger in a precise mathematical sense. You cannot assign the first object, the second object, the third object, and continue in a way that eventually reaches everything. This matters because the casual strategy of making one choice after another assumes that there is an after another that reaches the entire collection. If no such sequence exists, then the idea of working through the choices one by one does not solve the problem. The axiom of choice does not require you to work through them. It says the completed selection exists anyway. That is a very different claim. Imagine an enormous building filled with rooms. Every room contains at least one sealed box, and you want to select one box from every room. If the rooms are numbered in a simple sequence, you might imagine beginning with room 1, then room 2, then room 3. You never finish physically, but at least the pattern is clear. Now suppose the rooms are not given to you in any useful order. There is no first room, there is no master list, there is no natural way to say which room should come next. The building analogy begins to fail because a physical building automatically gives you geography. Rooms have locations. You could choose the northernmost room, or the one nearest the entrance, or invent some other system based on space. Mathematical collections do not have to provide that luxury. So remove the building. You're left only with a collection of non-empty collections. That stripped-down situation is exactly where the foundational issue lives. No shelves, no labels, no physical arrangement, no hidden geography. Only the information that every collection contains something. Is that enough? The axiom of choice says yes, a complete selection exists. The reason some mathematicians found this uncomfortable becomes easier to understand when we compare two kinds of mathematical proof. In a constructive argument, you do not merely learn that something exists, you're given a way to produce it. Perhaps the proof describes an algorithm. Perhaps it identifies a smallest object. Perhaps it builds the result step by step from things already known. There is something satisfying about this kind of proof because the object does not remain mysterious. You can see where it came from. A non-constructive argument can work differently. It can show that refusing the existence of an object would lead to a contradiction, or that logical conditions force at least one suitable object to exist, without ever telling you which object it is. Modern mathematics uses many non-constructive arguments quite comfortably. The axiom of choice is therefore not strange merely because it can prove existence without construction. The deeper issue is the enormous generality of what it permits. It allows this kind of existence across arbitrary collections, even when there is no unified method for producing the choices. For mathematicians who accepted a broad view of mathematical existence, this was not a problem. If logical principles guarantee an object, the object need not carry instructions for how a human being should find it. For mathematicians with more constructive instincts, that answer could feel incomplete. A selection that cannot be specified, calculated, described, or generated may seem less like an object we have discovered and more like an object we have allowed ourselves to assume. The disagreement became sharper because the axiom could be used in proofs where the chosen objects remained completely invisible. A mathematician might need one representative from each of infinitely many collections. Instead of identifying the representatives, the proof could simply appeal to choice, say that such a selection exists and continue. After that step, additional conclusions could be built on top of something no one had explicitly constructed. This is one reason the axiom feels almost modest when stated and much more powerful when used. The statement itself is about choosing. Its consequences are about what kinds of mathematical structures are allowed to exist. One useful example appears when mathematicians divide objects into groups according to some notion of equivalence. Perhaps several objects are considered essentially the same for the purpose of a problem. Each group may contain many members, and a mathematician may want to choose one representative from every group. If there are only finitely many groups, no problem. If the groups have natural representatives, no problem. If there are infinitely many arbitrary groups with no preferred member, then selecting one representative from every group may require the axiom of choice. The representative does not have to be special. It only has to be one member of the group. That sounds almost trivial, yet the selected representatives can form a new set with properties that are anything but trivial. This is where the axiom begins to create objects that seem difficult to connect with ordinary intuition. The selections can be so irregular that there is no simple description of the resulting set. It may exist only because choice says that one representative can be taken from each group. You should not imagine a hidden mathematician somewhere painstakingly making the decisions. There may be no decision process at all. The assertion is about existence, not activity. This is one of the most important conceptual shifts in the subject. We use the word choose because it sounds like an action, but in formal mathematics, the axiom does not describe a person choosing anything. It guarantees a mathematical object that behaves as though one selection has been made from each set. That may seem like a small linguistic point, but it removes many misleading pictures. Nobody's required to live forever. Nobody reaches the final set. Nobody performs infinitely many physical movements. The selection simply exists as a completed structure. Still, another question appears immediately. If the selection exists, can we describe it? Not necessarily. Can we compute it? Not necessarily. Can we explain why one particular object was selected instead of another? Again, not necessarily. This is where the axiom can feel very different from everyday choice. When you choose tea instead of coffee, there may be a reason. Perhaps you prefer tea. Perhaps it is late. Perhaps the coffee machine has made a noise suggesting that it would like the evening off. Choice in ordinary life often has a cause or criterion. Choice in the axiom does not need one. The selected objects need not share a pattern. There does not have to be a reason connecting them. One representative is taken from every set, and that is enough. This extreme freedom is part of what gives the axiom its strength. A rule based on choosing the smallest object works only when smallest makes sense. A rule based on choosing the first object works only when first makes sense. The axiom does not care whether either concept is available. It applies in situations where no convenient structure exists. That means it can reach places ordinary constructive methods cannot easily reach. There is a strange reversal here. The less structure the collections provide, the more valuable the axiom becomes. When everything is orderly, choice is unnecessary. When everything is chaotic, choice becomes powerful. Mathematicians discovered that this power was useful in many areas. In algebra, it helps establish the existence of certain bases. In analysis, it appears behind important results involving large spaces and collections. In topology, it supports general theorems that would otherwise require additional restrictions. Set theory, of course, places it directly among questions about infinity and ordering. What is fascinating is that a mathematician can spend years using results whose proofs depend on the axiom without ever thinking about socks, boxes, or mysterious selections. The axiom becomes part of the background, but when you examine the foundation closely, the same question is always sitting there. Can one object be selected from every non-empty set in an arbitrary collection? The usefulness of the answer yes makes it tempting to accept the principle without much hesitation. The trouble is that mathematics has learned to be suspicious of convenient assumptions. History contains many examples where something that seemed obvious turned out to hide a logical difficulty. The foundations of mathematics became a serious area of study partly because mathematicians wanted to know exactly which assumptions their arguments were using. Infinity made that need especially urgent. When dealing with finite objects, intuition is often reliable enough to guide us. Infinite collections can produce results that feel impossible even when they are logically correct. A classic example is the idea of an infinite hotel with every room occupied. In an ordinary hotel, full means no additional guest can be accommodated. In an infinite hotel with rooms arranged in a simple endless sequence, every current guest can be moved to the next room, leaving the first room empty. Nothing like this can happen in a finite building. The surprise comes entirely from infinity. The lesson is not that infinite hotels exist. The lesson is that words borrowed from finite experience can behave differently when mathematics pushes them into infinite settings. Choice is one of those words. If you can choose from each of 5 sets, it feels natural to assume that you can choose from each of infinitely many sets. But infinity has already taught us that natural extensions can be dangerous. Suppose someone tells you that every person in a finite crowd can be assigned a chair. You might reasonably believe that the whole crowd can be seated if there are enough chairs. With infinite collections, statements about individual possibility and global arrangement require more care. The axiom of choice is a rule that tells us one particular global arrangement is allowed. Its power becomes clearer when we ask what happens if we refuse to use it. This is a very useful way to understand any mathematical assumption. Instead of only asking what it gives us, ask what disappears without it. Without the full axiom of choice, some familiar results remain perfectly safe. Finite selections still work. Many countable selections can be handled under weaker assumptions. Collections with natural rules can still be managed. But certain broad statements about arbitrary sets can fail. There may be non-empty collections from which no complete selection can be proved using the remaining foundational assumptions. Notice the wording carefully. This does not necessarily mean that someone has found a physical collection where choice visibly fails. We're talking about what follows logically inside a formal mathematical system. That difference is essential. Foundational mathematics often concerns not only objects, but also the strength of the assumptions used to reason about them. If a conclusion cannot be proved without adding a certain principle, that tells us something about the logical architecture beneath the theorem. The axiom of choice turned out to occupy a remarkably central position in that architecture. Several statements that look unrelated are actually equivalent to it. One says, in effect, that every set can be arranged in an especially powerful kind of order. Another provides a way to find maximal objects under broad conditions. Others guarantee the existence of bases in very general spaces. At first glance, ordering, maximality, bases, and choosing representatives seem like separate topics. The surprising discovery is that they can carry the same logical strength. Accept one, and you can derive the others. This means that the question of choice cannot always be avoided simply by refusing to mention the axiom itself. A theorem may quietly bring the same assumption through another door. That made the historical debates more complicated. Mathematicians were not deciding whether they liked one isolated sentence. They were deciding whether they were comfortable with an entire network of equivalent principles and the mathematics those principles supported. Some wanted the power, some disliked the consequences. Many wanted both the useful theorems and a clearer understanding of exactly what they were committing themselves to. The question became particularly pressing because the axiom could produce objects with no ordinary method of construction. It is one thing to accept a hard-to-visualize mathematical object. Mathematics is full of those. It is another to accept an object whose existence depends precisely on permitting arbitrary selections that cannot be explicitly specified. These objects can behave in ways that seem almost designed to offend common sense. Soon the controversy would move beyond philosophy and into geometry. A sphere, an object that feels as familiar and well-behaved as geometry can possibly offer, would become the stage for one of the strangest consequences of unrestricted choice. The mathematics would claim that a sphere could be separated into a small number of highly unusual sets of points and rearranged into two spheres, each matching the original. That result did not appear because mathematicians had suddenly forgotten how volume works. It appeared because the pieces involved were nothing like ordinary physical pieces. They were created through selections so irregular that our usual ideas about measurable volume could no longer be applied to them. And behind the existence of those pieces stood the same principle we have been examining. Choose one representative from each appropriate collection. No explicit recipe for all the choices. No ordinary cutting process. No physical construction. Just existence. That is where the phrase choose one stops sounding harmless. The axiom does not merely help us select objects that were already sitting politely inside boxes. It can help create entirely new mathematical sets whose structure would be almost impossible to obtain by ordinary constructive means. Once such sets are available, conclusions can follow that would never occur in finite geometry. The unsettling part is not that mathematics makes a mistake. The unsettling part is that the logic works. Every step can be valid, and the final conclusion can still look completely unlike anything our physical intuition prepared us to expect. This is why the argument over choice was never simply about whether mathematicians were allowed to save themselves some work. It was about how much existence mathematics should permit when no construction accompanies it. It was about whether infinity should be treated as a completed landscape containing objects we may never explicitly identify. It was about whether logical consistency is enough reason to accept a mathematical world, even when that world contains objects with properties that feel deeply unnatural. And before the sphere duplication and the stranger consequences can make sense, there is one historical question worth understanding. Someone had to decide that this quiet principle of selection was important enough to state explicitly in the first place. It did not begin as an attempt to shock mathematics or produce paradoxes. It appeared because a mathematician was trying to solve a serious problem about infinite sets, and discovered that a seemingly obvious act of choosing needed to be written down as an assumption. The odd thing about the axiom of choice is that it did not enter mathematics because someone was searching for a controversial new principle. No mathematician woke up one morning and decided that the foundations of mathematics had been getting along far too peacefully. The problem appeared during an attempt to answer a question that had already been troubling mathematicians for years. A question about whether every possible set could be arranged in a particularly orderly way. By the beginning of the 20th century, infinity had become something mathematicians were studying directly, rather than merely mentioning when a sequence continued forever, and this created problems that earlier mathematics had rarely needed to confront. A central figure in this change was Georg Cantor, whose work on infinite sets had revealed that different infinite collections could have different sizes. This was already a difficult idea to absorb. A person could accept that the positive whole numbers continue forever, and that the points on a continuous line also continue without end. Yet Cantor showed that these two infinities were not the same size. There were, in a precise mathematical sense, more points on the line than there were positive whole numbers. Once mathematicians began taking results like this seriously, infinity stopped being a vague word meaning very large and became an object of careful study. Cantor also cared deeply about order. A set might contain many objects, but knowing what those objects are is different from knowing how they can be arranged. With a finite collection, arranging the objects is usually simple. Put 5 books on a shelf, and you can decide which book comes first, which comes second, and so on until the last one. The arrangement may be alphabetical, based on height, determined by the colour of the covers, or produced by whatever system seemed reasonable, before someone bought another book and ruined everything. Finite collections are cooperative in this way. Infinite collections require greater care. Some can be arranged so that there is a clear first member, followed by another, much like the positive whole numbers. But Cantor was interested in something stronger, an arrangement called a well-ordering. In a well-ordered set, not only does the whole collection have a first member, but every non-empty portion of that collection also has a first member according to the chosen ordering. This property is extremely useful because it gives mathematicians a way to reason through infinite sets in an orderly fashion, extending certain methods that feel familiar from ordinary counting into a much larger world. The difficulty was proving that every set could be arranged in such a way. For some sets, the answer was easy. The positive whole numbers already have the required order. Other collections can be rearranged into a suitable order without much difficulty. But the claim Cantor wanted was much stronger. It said that every set, regardless of its size or internal structure, could somehow be well ordered. Cantor regarded this as a fundamental principle, but producing a generally accepted proof was another matter. The question became important enough to appear in the famous collection of problems David Hilbert presented at the International Congress of Mathematicians in Paris in 1900. Hilbert was interested in the foundations of set theory, and in the unresolved questions surrounding the sizes and ordering of infinite sets. The issue of well-ordering was therefore not an obscure puzzle sitting quietly in a corner. It belonged to the central foundational discussions of the period when mathematicians were trying to understand exactly what could be said about the infinite objects that had entered their subject. A few years later, Ernst Zermelo entered the story. Zermelo was a German mathematician who had worked in several areas before becoming deeply involved in set theory. In 1904, he produced a proof that every set could be well ordered. The proof appeared in a remarkably short paper, whose title announced exactly what it intended to establish. The published piece was presented as coming from a letter addressed to Hilbert, and the paper occupied only a few pages. It was not physically large, which is useful evidence that mathematical controversy does not require generous amounts of paper. Zermelo's proof relied on a principle of selection. In simple language, he assumed that when dealing with a collection of non-empty sets, it was possible to associate with every set one of its members. This was the idea that would become known as the axiom of choice. Zermelo himself acknowledged that this principle could not simply be reduced to something obviously simpler within his argument, but he also pointed out that mathematicians were already using this kind of reasoning in many places, often without drawing much attention to it. In other words, he was not presenting choice as a bizarre invention imported from somewhere outside mathematics. He regarded it as a logical principle that had already been operating quietly in ordinary mathematical practice. That detail makes the controversy much more interesting. The axiom of choice did not suddenly introduce the act of arbitrary selection into mathematics. Mathematicians had been making arguments that involved choosing objects from collections before Zermelo gave the principle a prominent role. What changed was that the assumption had now been isolated, stated clearly, and used to prove a major theorem about arbitrary sets. A habit that had previously passed unnoticed was suddenly standing under bright lighting with everyone examining it. There is a familiar pattern here that extends far beyond mathematics. People can follow an unwritten rule for years without disagreement, but the moment someone writes the rule down, everyone discovers that they apparently have very strong opinions about it. Families manage this with holiday traditions. Offices manage it with kitchen etiquette. Mathematics managed it with infinite selection. Zermelo's use of choice attracted criticism almost immediately, because some mathematicians did not accept that such unrestricted selection was legitimate. Their concern was not usually that choosing one object from one non-empty set was impossible. The problem was the leap to an arbitrary collection of sets when no rules specified how the individual selections were made. The proof seemed to rely on a completed collection of choices while giving no general construction for producing those choices. This returned mathematics to the uncomfortable distinction we have already encountered. There is a large difference between saying that every individual choice is possible and saying that all those choices together determine a completed mathematical object. With finite collections, the difference is barely noticeable. With infinite collections, especially very large ones, it becomes essential. Zermelo did not abandon the argument when objections appeared. Instead, the debate encouraged him to examine the foundations more carefully. In 1908, he published a new proof concerning the possibility of well-ordering, addressing objections that had arisen around his earlier work. In the same year, he published a systematic investigation of the foundations of set theory, presenting a collection of axioms intended to control how sets could be formed and manipulated. Choice appeared within that foundational framework rather than remaining an informal principle used for one isolated theorem. This was happening during a period when set theory badly needed rules. Cantor's discoveries had opened a powerful new area of mathematics, but unrestricted reasoning about collections had also produced paradoxes. Mathematicians had learned that simply allowing any describable collection to count as a set could lead to contradictions. Set theory therefore needed boundaries. If sets were going to support the foundations of mathematics, mathematicians had to specify what operations were permitted and what kinds of sets could be assumed to exist. Zermelo's axiomatic approach was one response to this problem. Instead of saying that any collection anyone could describe automatically formed a legitimate set, mathematics would begin with certain basic assumptions and allow new sets to be obtained according to carefully stated principles. The goal was not to make mathematics more bureaucratic for the pleasure of it. The goal was to prevent contradiction while preserving enough mathematical power to continue doing useful work. The axiom of choice occupied an unusual position within the system because it did not look quite like the other rules. Many foundational axioms tell you how sets can be formed, combined, separated, or related. Choice gives permission of a different kind. It allows a selection to exist across a collection, even when no explicit selecting rule has been supplied. This difference helps explain why it attracted so much attention. If an axiom tells you that two existing sets can be combined into another set, the result feels relatively concrete. You know where the ingredients came from. If an axiom tells you that one representative can be chosen from every member of an arbitrary collection, the resulting selection may have no pattern that can be described at all. Zermelo's argument for accepting the principle was practical as well as philosophical. He emphasized that reasoning of this general kind was already present in mathematics. Rejecting the axiom would therefore not simply mean refusing one new trick. It would require mathematicians to reconsider proofs and habits they had previously regarded as acceptable. That put critics in an awkward position. If they objected to Zermelo's use of choice, they needed to decide exactly what kind of selection they were prepared to allow instead. Choosing from finitely many sets seemed safe. Choosing from an infinite sequence of sets might seem more reasonable when an explicit method was available. Choosing from arbitrary collections without any method was where resistance grew stronger. But drawing a perfect boundary between acceptable and unacceptable selection was not necessarily simple. The disagreement also revealed that mathematicians could mean different things by the word existence. Suppose a proof tells you that a certain object must exist because every alternative would lead to a contradiction. One mathematician may regard the matter as settled. Another may ask for an explicit construction before feeling satisfied. Neither attitude is merely a question of personality. They represent different views about what mathematical proof should accomplish. If mathematics describes an objective world of abstract structures, then there is nothing especially strange about objects existing, even when humans cannot construct them. We cannot expect every fact about an infinite mathematical universe to arrive with a convenient instruction manual. If mathematics is understood more constructively, the situation looks different. An existence claim should ideally come with a method. Saying that there must be an object somewhere without showing how to obtain it can appear weaker than actually producing one. The axiom of choice forced this philosophical difference into ordinary mathematical practice. It was difficult to dismiss the argument as irrelevant because the well-ordering theorem mattered, and the consequences of choice reached into many other fields. At the same time, it was difficult to treat the issue as purely practical, because the principle touched the deepest questions about what mathematical objects were allowed to exist. There is another reason the timing was important. Around the beginning of the 20th century, mathematics was going through a broader foundational crisis. Set theoretic paradoxes had raised doubts about informal reasoning with infinite collections. Different schools of thought were developing about logic, proof, and construction. Mathematicians were not merely arguing about how to solve individual problems. They were asking what mathematics was made of and what counted as a legitimate argument. Into that atmosphere arrived a proof saying that every set could be placed into an extraordinarily useful kind of order, provided one accepted a general principle of arbitrary choice. You can understand why the response was not a polite collective nod followed by tea. What made Zermelo's idea especially difficult to ignore was that the conclusion itself was extremely powerful. If every set can be well ordered, then even collections that seem completely structureless can be given an ordering with a first member in every non-empty portion. This means that, at least from the perspective of pure mathematics, no set is too chaotic to receive this kind of organization. Think about how strong that is. A set may contain objects that have no natural comparison at all. There may be no intuitive reason for one member to come before another. Yet the well-ordering theorem says that some suitable ordering exists. It does not necessarily tell you what that ordering looks like. That should now sound familiar. The same style of existence appears again. A structure is guaranteed, but no explicit description may be available. In ordinary finite life, arranging things means performing an arrangement. If you tell me that all the books in a room can be placed in a particular order, I expect that with enough patience we could put them on shelves and look at the result. For arbitrary infinite sets, the theorem can guarantee an ordering that no person could ever write down in full, and that may not be definable by any simple rule. This was not an accidental side effect of Zermelo's proof. It reflected exactly the strength of the choice principle supporting it. An arbitrary choice was being used to produce an arbitrary order. The relationship between the two became fundamental. The axiom of choice and the statement that every set can be well ordered were eventually recognized as equivalent in the standard framework. If you have the axiom of choice, you can establish the well-ordering theorem. If you have the well-ordering theorem, you can recover the ability to make the selections required by choice. This equivalence tells us something important about why the original controversy became so persistent. The axiom was not merely one possible method Zermelo happened to use. It expressed mathematical strength that was deeply connected to the conclusion itself. Suppose you want to choose one object from every set in some collection. If the relevant universe of objects can be well ordered, then each non-empty set has a first member under that ordering. You simply select that first member. The mysterious arbitrary choice is replaced by an order that tells you what to take. Of course, obtaining that order for every possible set is exactly where the power has gone. Mathematics has not made the difficulty disappear, it has moved it. This happens often in foundational mathematics. Two statements can look very different while hiding the same logical commitment. One talks about choosing representatives, another talks about ordering sets. A third may later talk about maximal elements in abstract structures. Proving that these principles are equivalent reveals that they are different faces of the same underlying assumption. For someone trying to avoid choice, this can become inconvenient. You may refuse the axiom itself only to discover that another theorem you particularly enjoy carries essentially the same baggage. Mathematics is very patient about such things. It allows you to inspect the baggage before deciding whether to board. The controversy following Zermelo's work therefore became useful, even for mathematicians who eventually accepted choice. It forced the community to identify where the assumption was being used. Proofs could be examined more carefully. Researchers could ask whether a result required the full axiom or only some weaker form of selection. They could compare what remained true with and without additional assumptions. That practice eventually became an important part of set theory. Instead of treating all uses of infinity as one large philosophical problem, mathematicians learned to measure the logical strength of particular statements. Some conclusions require very little choice. Others need stronger forms, some are equivalent to the full axiom, and some can be proved without it at all. The resulting picture is far more interesting than simply declaring choice correct or incorrect. It shows that foundational assumptions form a landscape. Different mathematical worlds can be explored by changing which assumptions are present. Zermelo could not yet know how far this idea would eventually go. The deepest results about the independence of the axiom would arrive decades later. What he had done was isolate the principle clearly enough for mathematics to begin asking the right questions. Before 1904, selection from arbitrary collections could appear as an informal step that passed without much comment. After Zermelo's proof, the issue had a name, a purpose, and a prominent place in foundational debate. That transformation is perhaps the strangest part of the axiom's birth. The controversial idea was not created by making mathematics more complicated. It was created by noticing that something mathematicians considered obvious might actually be an assumption. There is a lesson in that. The most interesting foundational questions often begin when someone points at a familiar step and asks why it is allowed. Why can we choose one object from each collection? Why can every set be ordered? Why should an object count as existing when we cannot construct it? Questions like these can sound unnecessarily cautious until infinity enters the discussion. Then every innocent word begins carrying more responsibility than expected. Zermelo's principle survived the first objections, but the objections did not disappear. Instead, they became part of a larger investigation into how much mathematics depends on choice and how different the subject becomes when choice is removed. The next difficulty comes from something we've touched repeatedly without examining closely enough. We keep talking about infinite sets as though infinity were one environment with a few unusual habits, but set theory revealed a much stranger situation. There are different kinds of infinity, different ways of arranging them, and collections so large that the simple picture of counting one object after another no longer applies. Once those infinities are taken seriously, the real strength of the axiom of choice becomes much easier to see, along with an even more unsettling fact about its status within mathematics. It is powerful enough to reshape huge parts of the subject, yet the ordinary rules of set theory cannot simply force us to accept it. Infinity is one of those ideas that seems simple until mathematics asks you to be precise about it. In ordinary conversation, infinity usually means something that keeps going forever. You might imagine counting without ever reaching a final number, walking along a road that has no end, or listening to someone explain the terms and conditions of a new piece of software. The general feeling is clear enough. There is always more. Mathematics discovered, however, that this familiar picture captures only one small part of what infinity can be. The positive whole numbers provide the easiest place to begin. You can start with 1, continue to 2, then 3, then 4, and keep going without stopping. There is no largest positive whole number because whatever number you choose, another one comes after it. This collection is infinite, but it has an important kind of order. You can imagine listing its members one after another. Every number has a particular place in the list, and although the list never ends, the process itself is easy to understand. Now consider the even positive whole numbers. At first glance, there seem to be fewer of them. After all, the even numbers are only part of the full collection of positive whole numbers. Half the numbers appear to be missing. Infinity immediately refuses to behave like a finite collection. You can match every positive whole number with exactly one even positive whole number. The first positive whole number matches the first even number. The second matches the second even number. Continue this pattern, and every positive whole number receives a partner, while every even positive whole number is used exactly once. This means the collection of all positive whole numbers and the collection of all positive even numbers have the same size in the mathematical sense used for infinite sets. That would be impossible with finite collections. If you have 10 biscuits and remove half of them, you do not still have 10 biscuits, unless someone in the room is using a very optimistic accounting system. With infinity, a proper part of a collection can contain just as many members as the whole collection. This strange behaviour led mathematicians to develop a precise way of comparing the sizes of sets. Instead of relying on ordinary counting, they asked whether the members of two sets could be paired perfectly. If every member of one set can be matched with exactly one member of the other, with nothing left over on either side, then the sets are considered the same size. This method works beautifully for finite sets, but it also works when counting in the ordinary sense is impossible. Using this idea, the positive whole numbers turn out to have the same size as many collections that initially seem much larger. The whole numbers, including negative values, can still be arranged into a list. Fractions can also be organised so that, with enough care, every fraction eventually appears somewhere. These collections are infinite, but they are what mathematicians call countable. The word does not mean that anyone could actually finish counting them. It means their members can, in principle, be arranged in a sequence corresponding to the positive whole numbers. Then Georg Cantor discovered something much stranger. The points on a continuous line cannot be listed this way. No matter how cleverly you try to arrange all the numbers represented by points along a line into a sequence, there will always be numbers missing. Cantor showed that this collection is genuinely larger than the collection of positive whole numbers. Infinity therefore comes in different sizes. That sentence is so familiar in modern mathematics that it is easy to forget how unsettling it once seemed. For centuries, infinity had often been treated as a general idea of endlessness. Cantor turned it into a landscape containing distinct levels. Once that landscape appears, the axiom of choice becomes much more important. If every infinite collection behaved like the positive whole numbers, then many selection problems would be easier to imagine. You might hope to arrange everything into a long list, and work through the list in order. Even if the process never physically ended, at least there would be a clear rule describing which object came first, which came second, and what happened next. But some collections are too large to fit into such a sequence. There may be no way to arrange their members as first, second, third, and so on while eventually including everything. This matters because the phrase "choose one object at a time" quietly assumes that the things you are choosing from can themselves be organised into a suitable order. If they cannot, then the familiar mental picture of making choices one after another is no longer available. The axiom of choice does not care. It does not require the collection to be countable. It does not require a natural order. It does not require a method that reaches each set in sequence. It simply says that if you have a collection of non-empty sets, a selection containing one element from every set exists. The larger and less structured the collection becomes, the more remarkable this permission is. To understand why, imagine a collection of boxes that can be numbered one after another. Even if there are infinitely many, you can at least describe the boxes using the positive whole numbers. Perhaps you could choose from the first box, then the second, and continue according to the numbering. Now remove the numbering. Suppose there are so many boxes that they cannot even be arranged into an ordinary endless list. There is no first box given to you. There is no second box waiting behind it. There is no simple sequence telling you how to proceed. Each box contains at least one object, but no general rule tells you which object to choose. The axiom of choice still allows a completed selection. It gives mathematics an object that contains one chosen member from every box, even though there may be no procedure that could move through the collection in ordinary sequence. This is one reason choice is closely connected to questions about ordering. If every set could be arranged into an especially strong kind of order, then making selections would become easier. You could simply take the first available object according to that order. But saying that every set can be ordered in this way is itself a very powerful claim. In fact, as mathematicians eventually established, the statement that every set can be well ordered carries the same logical strength as the axiom of choice. The mystery has not disappeared, it has changed clothes. Instead of asking how you can choose one element from every arbitrary set, you can ask how you can impose a suitable order on every arbitrary set. Either way, you are making a strong claim about infinite collections. This is where set theory becomes less like ordinary arithmetic and more like a study of possible mathematical worlds. A foundational system begins with axioms. These are basic assumptions that are not proved inside the system from earlier statements. They are the starting rules from which other results are derived. This may initially sound uncomfortable. We're used to thinking of mathematics as the subject where everything is proved. Surely allowing unproved assumptions at the beginning seems like sneaking something through the back door. But every logical system needs a starting point. If every statement had to be proved from something earlier, you would never reach the beginning. Eventually, mathematics must say that certain basic rules are being accepted, and reasoning proceeds from there. The important question is not whether there are axioms. The important question is which axioms we choose and what follows from them. After the difficulties created by unrestricted early set theory, mathematicians developed carefully controlled systems of axioms, describing how sets could exist and interact. The system associated with Ernst Zermelo and Abraham Frankl became the standard foundation used across much of modern mathematics. When the axiom of choice is included, the full framework is often referred to by a shortened name, but the important point for us is simpler. There is a collection of standard rules for set theory, and choice can be added alongside them. For some time, mathematicians naturally wondered whether that additional step was really necessary. Perhaps the axiom of choice could eventually be proved from the other axioms. If so, then choice would not genuinely be optional. It would simply be a hidden consequence of principles mathematicians had already accepted. That would have made the philosophical disagreement much easier to settle. Suppose someone objects to the axiom because arbitrary infinite selection feels suspicious. If another mathematician can prove choice using assumptions the critic already accepts, then the argument changes completely. The critic would either have to accept choice or reject one of the earlier assumptions as well. There was another possibility. Perhaps choice could be disproved. Maybe accepting it would eventually produce a contradiction, showing that the principle was simply incompatible with a reliable foundation for mathematics. If that happened, the controversy would also end. There would be no need to debate whether the axiom was philosophically attractive, because mathematics would have rejected it on logical grounds. Neither of these outcomes occurred. The first major result came from Kurt Gödel during the 20th century. Gödel had already transformed mathematical logic by showing that sufficiently powerful formal systems have unavoidable limitations. In work on set theory, he showed that if the standard axioms of set theory without choice are consistent, then adding the axiom of choice does not create a contradiction. In other words, the other axioms cannot disprove choice, assuming the foundational system is itself free from contradiction. This was a profound result. It meant that mathematicians hoping to demonstrate that the axiom of choice was logically impossible would not succeed using the ordinary axioms of set theory. Choice could live peacefully alongside them, but that still left another possibility. Perhaps choice was consistent with the other axioms because it was actually provable from them. That question remained open until Paul Cohen developed a new method in the 1960s. Cohen showed that, again assuming the standard axioms are consistent, those axioms cannot prove the axiom of choice either. Together, the results of Gödel and Cohen established the independence of the axiom of choice from the remaining standard axioms of set theory. This is a remarkable situation. The usual foundational rules do not force choice to be true. They also do not force choice to be false. You can build mathematical models in which the standard rules hold and the axiom of choice is accepted. You can also build models in which the same underlying standard rules hold, but choice fails. The word model here does not mean a small physical replica sitting on a desk. It means a mathematical interpretation in which the axioms are satisfied. What these results tell us is that the standard rules allow more than one possible mathematical universe. In some of those universes, arbitrary choice is available. In others, it is not. There is something almost perfectly appropriate about the conclusion. After decades of argument over whether mathematicians should accept a principle of choice, mathematics itself answered by refusing to choose for them. the foundational system says, in effect, that both routes are available. This does not mean that truth has become meaningless, or that mathematicians can simply declare anything they like. Far from it. Once you specify which axioms you are using, strict logical consequences follow. You cannot decide halfway through a proof that a contradiction would be more convenient and simply invite one in. The flexibility exists at the level of the foundational assumptions. Choose one system, and certain theorems become available. Choose another, and the landscape changes. This is similar to what happens in geometry. For a long time, mathematicians treated one particular statement about parallel lines as a natural part of geometry. Attempts were made to derive it from other assumptions. Eventually, mathematicians discovered that alternative geometries could be built by changing that assumption while preserving logical consistency. The result was not the destruction of geometry. It was the discovery that there were multiple geometrical systems. Something related happens with the axiom of choice. Instead of asking only whether choice is true in some absolute informal sense, mathematicians can ask what follows if it is accepted, and what follows if it is rejected. That shift turns a philosophical argument into a mathematical research program. What happens to infinite sets without full choice? Which useful theorems survive? Which fail? Can weaker versions of choice recover some results without introducing the full strength of the axiom? These questions reveal that choice is not simply an on and off switch. There are weaker principles that permit certain forms of selection without allowing everything the full axiom permits. For example, one can consider situations where the collection itself can be arranged in an ordinary sequence. Choosing one element from every set in such a sequence requires less strength than arbitrary choice over completely unrestricted collections. This distinction matters because some parts of mathematics need only weaker forms. A theorem may not require the entire axiom of choice. It may need only enough selection to handle a particular kind of infinite collection. Mathematicians can therefore study exactly how much choice a result uses. This is rather different from the early days, when the principle appeared as one broad and controversial assumption. The modern view is much more detailed. Choice has levels. Some are accepted even in frameworks that reject the unrestricted axiom. Others bring back nearly all of its power. The logical relationships among these principles form an entire subject of study. There is also a curious effect on familiar properties of sets. With the full axiom of choice, every set can be well ordered. Without it, there can be sets for which no such ordering is available within the model being studied. With choice, many statements about comparing the sizes of sets become especially clean. Without it, the world of infinite sizes can behave in ways that are much less tidy. This is an important reminder that the axiom does more than permit individual selections. It imposes a remarkable degree of organization on the infinite universe. Accepting choice means accepting that even the most unruly set can, in principle, be arranged into a well-ordering. It means accepting that certain maximal structures exist even when no constructive method produces them. It means accepting broad existence statements throughout mathematics. That is why the principle became so useful. It is also why the consequences can become so strange. The phrase one element from each set sounds modest, but once it applies to collections of enormous size and almost no structure, it becomes capable of producing objects that ordinary intuition would never suggest. One of the best ways to see this is through the real number line. The real numbers represent the continuous quantities we encounter in geometry and measurement. Between any two distinct real numbers, there are more real numbers. No matter how closely you zoom in, the line remains densely populated. The collection is not countable. It cannot be arranged into an ordinary list that eventually reaches every member. Now imagine dividing this enormous collection into groups according to some mathematical relationship and asking for exactly one representative from each group. There may be no natural representative, no smallest member, no first member, no obvious pattern. Using choice, however, you may still select one. The set of representatives you obtain can be astonishingly irregular. So irregular, in fact, that some familiar ideas about length and measurement no longer behave the way you expect. This does not mean that rulers suddenly stop working. It means that set theory can create collections of points that are not ordinary geometric objects. They are not intervals, smooth shapes, or anything you could physically draw. Their existence depends on forms of selection that provide no simple construction. Once those kinds of sets become available, mathematics can begin doing things that sound impossible when translated carelessly into the language of physical objects. This is the background behind the most famous consequence associated with the axiom of choice. The result does not begin with a magician's sphere. It begins with infinity, symmetry, and the ability to choose representatives from extremely complicated collections of points. The pieces produced are nothing like pieces of fruit or wood. They cannot be assigned ordinary volumes in the way familiar solid pieces can. That distinction matters enormously because without it, the result sounds like mathematics is claiming that matter can be duplicated. It is not. Still, even after every warning has been given, the theorem remains wonderfully unsettling. A solid mathematical ball can be divided into a small finite number of highly unusual point sets. Those sets can then be moved and rearranged so that they form two balls, each matching the original in size. The conclusion became known as the Banach-Tarski paradox. It does not contradict the axioms being used. It does not reveal an error in arithmetic. It does not provide a method for doubling an orange. It reveals what can happen when infinite sets, geometric symmetry, and the axiom of choice are allowed to work together without the restrictions that physical matter normally imposes. And this is the moment where the controversy becomes much easier to feel. So far, choice has sounded philosophical. It has concerned abstract questions about existence, construction, and whether the standard axioms can settle the issue. The Banach-Tarski result gives those questions a shape, a sphere. A familiar object is taken into the world of unrestricted infinite selection, and what comes back looks almost impossible. To understand why it is not a contradiction, we have to forget everything a kitchen knife teaches us about cutting things into pieces, because the pieces used in this argument are not pieces in any ordinary physical sense at all. Of all the strange consequences connected with the axiom of choice, one has become far more famous than the others because it manages to take a difficult question about infinite sets and turn it into something you can picture immediately. Imagine that you are holding a perfectly solid mathematical ball. It is an ordinary three-dimensional ball with a definite size and nothing unusual seems to be happening. Now imagine separating that ball into a small finite number of pieces, moving those pieces around without stretching them and putting them back together. What should you expect to get? Common sense suggests that you should end with one object containing exactly as much volume as you started with. Mathematics agrees with this in almost every situation we encounter in ordinary geometry. The Banach-Tarski paradox says that there are extremely unusual ways of dividing the ball so that the pieces can instead be rearranged into two balls, each the same size as the original. Stefan Banach and Alfred Tarski published the result in 1924 while studying finite decompositions of point sets in three-dimensional space. If that sounds impossible, that is a very sensible reaction. If you cut an orange into pieces and rearrange them, you cannot create two oranges of the original size unless you have quietly introduced another orange while no one was looking. Conservation of matter is not optional simply because the fruit is being handled by a mathematician. The Banach-Tarski result does not claim that physical objects behave this way. It concerns mathematical sets of points, and the word pieces is doing a great deal of work. These pieces are not ordinary chunks. They do not have smooth boundaries. They cannot be cut out with a knife. They cannot be manufactured, and they cannot even be assigned ordinary volume in the usual mathematical sense. The original theorem is about decomposing suitable sets in three-dimensional Euclidean space into finitely many subsets that can be moved rigidly and reassembled into another set, and a solid ball provides the most famous example. That distinction is the first thing to keep nearby because without it the paradox becomes a magic trick. The sphere is not being stretched. The pieces are not being enlarged. No point is secretly copied. Every point that appears at the end was already present at the beginning. What changes is the arrangement, and the reason this is possible lies in the extraordinary structure of the pieces themselves. We are dealing with collections containing infinitely many points arranged in patterns so irregular that our normal rules about volume no longer apply to them. If you're picturing 5 strange wedges sitting on a table, you're already making the pieces much too reasonable. To understand how something this odd can happen, begin with a simpler fact about infinity. Imagine a hotel with an ordinary finite number of rooms. If every room is occupied, there is nowhere to place another guest. Now imagine a hotel whose rooms correspond to the positive whole numbers. Every room is occupied, but another guest arrives. The manager can move the guest from the first room into the second, the guest from the second into the third, and continue the same pattern throughout the hotel. The first room becomes empty even though no guest has been removed. An infinite collection can therefore be matched with a proper part of itself in a way that a finite collection cannot. Banach-Tarski takes this general strangeness much farther. The ball contains infinitely many points, but simply having infinitely many points is not enough. A normal interval on a line also contains infinitely many points, and you cannot usually chop an interval into a few ordinary pieces and rearrange those pieces into 2 intervals of the same original length. Something more subtle is needed. The crucial ingredient comes from the symmetries of 3-dimensional space, especially rotations, together with a way of grouping points according to how those rotations move them. Imagine placing a point on the surface of a sphere and rotating the sphere. The point moves to another location while remaining the same distance from the center. Perform another rotation and it moves again. If you allow carefully chosen rotations to act repeatedly, one starting point can generate an entire collection of related points. Mathematicians can group together points that can be reached from one another through these combinations of rotations. Instead of thinking about individual points separately, you begin thinking about enormous families of points tied together by the allowed movements. The important rotations are chosen so that their combinations behave with remarkable freedom. Roughly speaking, different sequences of those rotations can lead to genuinely different movements, rather than repeatedly collapsing into the same result. That structure allows the points associated with those rotations to be organized in a way that resembles a branching network. If you imagine standing at one point in that network, different rotation choices send you down different branches, and those branches themselves keep producing more branches. The picture is not a literal drawing on the sphere, but it gives a useful sense of why 3-dimensional rotations provide enough complexity for the paradox. A similar idea had appeared earlier in work by Felix Hausdorff, who found a paradoxical decomposition involving the surface of a sphere. Banach and Tarski developed these ideas further and obtained their stronger result for bounded sets with interior in 3-dimensional space. Their paper states, in a much broader form than the popular ball story, that suitable bounded sets in at least 3 dimensions can be finitely decomposed into pieces that correspond under rigid movements. Now the axiom of choice returns, because after the points have been grouped into these enormous families, mathematics needs a way to select representatives. Imagine that the surface has been divided conceptually into countless collections of related points. From every collection, you want to choose one representative point. There may be no natural representative. There is no smallest point, no brightest point, and certainly no point wearing a small badge announcing that it has volunteered. The groups are abstract and highly complicated. This is exactly the kind of situation where the axiom of choice becomes useful. Choice allows mathematics to take one representative from every relevant collection without providing an explicit rule identifying all of those representatives. Once those representatives are selected, the rotations can be used to generate the strange sets required for the decomposition. In the standard Banach-Tarski construction, the resulting pieces cannot all possess ordinary Lebesgue volume. If they did have ordinary volumes that behaved normally under rigid movement and finite addition, the duplication would immediately create a contradiction. A ball of one volume could not become two balls each with that same volume. The escape from contradiction is that these pieces are non-measurable in the required sense. The word non-measurable can sound as though mathematicians have simply misplaced the ruler, but it means something much more precise. Ordinary geometric sets have volumes that behave in familiar ways. If you divide a box into two normal pieces, the volumes of the pieces add to the volume of the original box. Move a piece across the room, and its volume does not change. These properties are so natural that we rarely notice them. They are exactly what makes physical cutting and rearranging predictable. The strange Banach-Tarski pieces fall outside the class of sets to which this ordinary notion of volume can consistently be assigned. You cannot say that one piece contains a particular ordinary volume and then add those volumes together as though they were chunks of clay. The pieces are too irregular. They are dispersed through the original ball in a structure that is not remotely like a familiar solid region. Calling one of them a piece is technically correct, but it encourages a picture that mathematics does not actually provide. Imagine separating every individual point of a ball according to an enormously complicated membership rule, so that points belonging to the same piece are scattered throughout the object. Between points from one piece, you may find points from other pieces, and the structure continues at scales far beyond anything a physical cutting process could isolate. Even this picture should be treated cautiously, because the sets are not being generated by an ordinary algorithm you could simply run with smaller and smaller tools. Their existence depends on selection principles that do not produce a usable construction. This is why improving technology would not help. You cannot say that perhaps future humans will develop sufficiently precise lasers and eventually perform the Banach-Tarski decomposition on a football. Precision is not the obstacle. A physical object is made of atoms and other physical structures, not an actual continuum of mathematical points behaving exactly like an ideal geometric solid. More importantly, the required subsets are not physically separable regions. No matter how sharp your knife becomes, it still cuts along physical locations. It does not select an abstract collection containing scattered points chosen through an infinite set theoretic construction. The paradox therefore lives entirely within mathematics, but that does not make it trivial. Quite the opposite. Its importance comes from the fact that all the strange behaviour follows from rules mathematicians are willing to consider legitimate. No law of arithmetic is violated, no point is counted twice. The rigid movements used in the construction preserve distance. The surprise comes from combining infinite sets with a powerful form of selection, and then assuming that our finite intuition about volume should continue working on every subset produced. It does not. There is a useful comparison with ordinary numbers. If you add a finite collection of positive quantities, the total cannot remain unchanged when you duplicate every term. With infinite collections, familiar arithmetic instincts can fail. The positive whole numbers are the same size as the even positive whole numbers, even though the even numbers form only part of the original collection. Banach-Tarski is not the same phenomenon, but it belongs to the same broad lesson. When infinity becomes a completed mathematical object, relationships that are impossible in finite settings can become possible. The role of three-dimensional space is also important. Banach and Tarski showed a fundamental difference between the behaviour available in 3 or more dimensions and what happens in 1 or 2 dimensions under the corresponding kind of finite decomposition. Their original paper explicitly notes that the analogous theorem does not hold in the same way in 1 or 2 dimensional Euclidean space. This is not because circles and flat shapes are somehow better behaved morally. The difference comes from the structure of the groups of rigid motions available in different dimensions. 3-dimensional rotations are complicated enough to contain the kind of free behaviour needed for the classic paradoxical construction. In the plane, rigid movements do not provide the same structure. So if you are hoping to begin more modestly by duplicating a mathematical pancake before attempting the full mathematical orange, the geometry is less cooperative than you might expect. There is another point that often causes confusion. The phrase duplicating a sphere is commonly used when describing Banach-Tarski, but the famous popular version normally concerns a solid ball, meaning the interior together with its boundary. Related paradoxical decompositions also apply to the surface of a sphere, and Hausdorff's earlier work focused on that setting. The exact mathematical statements can therefore vary depending on whether someone is discussing the surface, the solid ball, or the broader theorem concerning bounded sets with interior. The important feature for our story is that three-dimensional geometry permits finite decompositions, with consequences that completely defeat ordinary ideas about preserved volume. A common modern presentation says that the solid ball can be decomposed using 5 pieces. 5 is striking because it sounds so small. If the theorem required an unimaginably large number of pieces, the result might feel slightly less offensive to intuition. 5 sounds like something you could place on a dinner plate, but again, the number of pieces is misleading because each piece is itself an enormously complicated, infinite set of points. Counting the pieces tells you almost nothing about how wild those pieces are. Think of a book containing infinitely many letters scattered across infinitely many pages, except the pages are also infinitely detailed, and every letter belongs to a pattern determined by transformations of the entire book. Saying that the construction has only a few pieces would be like saying you have simplified the library because you placed all the letters into 5 boxes. The number of boxes may be small, while the contents remain impossible to describe individually. This is one reason the axiom of choice can produce such powerful consequences. It does not need to give the selected objects a nice pattern. A constructive rule would usually impose some structure, because the rule itself describes why each element belongs where it does. Arbitrary choice can create selections with no simple global description. When those selections are used as the seeds for further operations, the resulting sets can be extraordinarily irregular. That irregularity is not a mistake accidentally introduced by a poor proof. It is essential. If all the Banach-Tarski pieces were ordinary measurable solids, the result could not happen. Their very strangeness is what allows the decomposition to escape the volume calculation that would otherwise stop it immediately. Suppose, only for intuition, that the original ball had some familiar volume. If it were divided into normal measurable pieces, you could add the volumes of those pieces and recover the volume of the ball. Rigidly moving the pieces would not change any of their volumes. Adding them after rearrangement would therefore produce exactly the same total volume. 2 balls of the original size would require twice as much, so normal measurable pieces cannot possibly do the job. Banach-Tarski avoids that reasoning because the required pieces are not all measurable in this sense. The ordinary volume calculation cannot even begin. Asking for the volume of one of those sets is rather like asking for the northwestern corner of a melody. The question assumes a property that the object does not possess in the required mathematical framework. That does not mean mathematicians can use non-measurable sets to make any absurd statement they like. The construction obeys very strict conditions. The pieces must be disjoint, they must collectively contain exactly the points of the original object, and the rearrangement uses rigid motions. The remarkable result is that sets satisfying all those requirements exist. Banach and Tarski did not present their work as a party trick. Their 1924 paper concerned a general theory of decomposing point sets into congruent parts, and the now famous paradox emerged from serious questions about measure, geometry, and equivalence. What later audiences remembered was naturally the part involving one ball becoming 2, because foundational set theory becomes much easier to discuss when it appears to threaten the fruit bowl. The result also explains why some early mathematicians were uneasy about unrestricted choice. If a principle allows you to prove the existence of sets that behave this strangely, perhaps, they thought, mathematics should be more cautious about accepting it. The Banach-Tarski paradox became a vivid example in arguments about whether non-constructive objects deserve the same status as objects that can actually be described or generated. Supporters could answer that strangeness is not contradiction. Mathematics has no obligation to make every infinite object resemble something found in a kitchen. If the axioms are consistent and the reasoning is valid, an unintuitive theorem may reveal a limitation of human intuition rather than a flaw in mathematics. That answer has become increasingly familiar as modern mathematics and physics have developed. Human intuition was built for medium-sized objects moving at low speeds over short distances. It was not designed for infinite point sets, curved space-time, quantum particles, or hotel managers responsible for infinitely many rooms. When the mathematics departs from ordinary experience, expecting our first instinct to remain reliable may be the more unreasonable assumption. Yet Banach-Tarski continues to feel unusually provocative because volume seems so basic. If you have 1 litre of water, you do not rearrange the molecules and obtain 2 litres of identical water. Our experience of physical quantity is closely tied to conservation. The paradox deliberately places an abstract mathematical object into language borrowed from that physical experience, and the mismatch creates the shock. Once you remember that a mathematical solid is not a physical object, the contradiction fades. A mathematical ball is an uncountable collection of ideal points. Those points have no individual physical size. Volume belongs to suitably well-behaved collections of them, not to each point separately. And not every possible collection of points has to be well-behaved. The axiom of choice greatly expands the kinds of collections we can assert exist. Some of those collections fall outside ordinary measurement. Combine them with the special structure of 3-dimensional rotations and the familiar connection between cutting, moving, and preserving total volume breaks down. There is an almost amusing lesson hidden inside the whole affair. We began with an axiom that seemed to say something modest about selecting one object from each collection. We followed that permission into infinite sets, where those selections could be made without explicit rules. We then used such selections to build objects that cannot be assigned ordinary volume, and those objects allowed a sphere to be decomposed in a way that makes one copy look like 2. At no stage did anyone add a rule saying spheres may now reproduce. The strange conclusion emerged from ideas that looked individually reasonable. This is often how foundational mathematics becomes interesting. The unsettling result is not caused by an obviously outrageous assumption. It appears when several ordinary-sounding principles interact in a setting far removed from ordinary experience. The axiom of choice says certain selections exist. Infinite set theory says collections can be vastly larger and stranger than finite intuition suggests. Geometry says rigid rotations preserve distance. Put those ideas together carefully enough, and the result is Banach-Tarski. For many mathematicians, this does not provide a reason to abandon the axiom. Instead, it provides a reason to understand exactly what the axiom gives us. Mathematics can distinguish between measurable and non-measurable sets. It can identify which arguments require choice. It can study weaker forms of choice and investigate what happens when choice is removed entirely. That last possibility is especially important, because once people encountered consequences like Banach-Tarski, an obvious question remained. What if we simply refused to allow the assumption that helped produce these objects? Would the paradox disappear? And if so, what else would disappear with it? The answer is not as simple as removing one troublesome theorem. The axiom of choice is tied to results that mathematicians use throughout many areas, and abandoning it changes more than the fate of one very unfortunate sphere. It also changes how certain infinite sets can be ordered, whether some mathematical structures are guaranteed to exist, and what kinds of representatives can be selected from arbitrary collections. That is why the historical disagreement became so intense. Banach-Tarski supplied a memorable example of what critics disliked, but supporters could point to an enormous collection of useful results that choice made possible. Mathematics was being asked to decide whether strange consequences were a price worth paying for a powerful principle of existence, and different mathematicians had very different ideas about what the word existence should be allowed to mean. By the time results like Banach-Tarski had entered mathematics, The argument surrounding the axiom of choice was no longer a quiet disagreement about a technical detail. The principle had begun as a simple permission to select one object from every non-empty collection, but mathematicians now understood that accepting this permission could influence enormous parts of the subject. It could guarantee the existence of objects no one could explicitly construct, place structure on sets that appeared to have no natural order, and contribute to results so far removed from physical intuition that a mathematical ball could be rearranged into two copies of itself. For some mathematicians, this was evidence of the extraordinary reach of abstract reasoning. For others, it was precisely the reason to become suspicious. The disagreement was not really about whether choice was useful. Almost everyone could see that it was useful. The difficult question was whether usefulness was enough reason to accept a principle at the foundations of mathematics. If a rule makes thousands of proofs easier, but also allows objects that cannot be described or constructed, should mathematics embrace it? If removing the rule makes mathematics more restrictive but perhaps more closely connected to explicit procedures, is that restriction a weakness or a virtue? These questions became part of a much larger debate about what mathematics was supposed to be. To understand the intensity of the disagreement, it helps to remember that the early 20th century was already an uncomfortable period for the foundations of mathematics. Set theory had opened a new world of infinite objects, but it had also exposed serious logical problems. Mathematicians had discovered that careless reasoning about collections could produce contradictions. The confidence that mathematics rested on completely obvious foundations had been shaken, and researchers were trying to rebuild those foundations with much greater precision. In that atmosphere, an axiom allowing arbitrary infinite selections was unlikely to pass unnoticed. Ernst Zermelo regarded the principle as natural and mathematically necessary. He had used it to prove that every set could be well ordered, and he argued that comparable forms of selection had already appeared in mathematical reasoning before anyone had bothered to isolate them as a separate assumption. From this perspective, the axiom of choice was not an artificial invention. It was an honest statement of something mathematicians were already doing. That argument had considerable force. If mathematicians had been using a principle implicitly, perhaps stating it openly was an improvement rather than a problem. Mathematics could now track exactly where the assumption entered a proof, instead of allowing it to hide inside informal phrases such as select one representative from each collection. The critics, however, were concerned about exactly what Zermelo's principle allowed once it was stated without restrictions. Choosing from a finite collection was not controversial. Choosing from an infinite collection when there was an explicit rule was usually not the main problem either. The objection appeared when mathematics claimed that a complete selection existed, even though no procedure identified the choices. This brought the debate back to the meaning of mathematical existence. Suppose you tell me that a certain number exists, and then give me a method for calculating it. That kind of existence feels very solid. I may not have carried out the calculation yet, but I know what needs to be done. Suppose instead that you prove that some number with a particular property must exist, while your proof gives no way to find it. Most modern mathematicians are comfortable with many arguments of this kind, but the philosophical difference is still real. The first proof gives you both existence and construction. The second gives existence alone. The axiom of choice seemed to permit this second kind of existence on a very large scale. It could assert that an enormous collection of representatives existed without identifying any general mechanism for producing them. For critics with constructive instincts, this felt dangerous. They worried that mathematics was filling its universe with objects that could never be reached through explicit operations. If those objects then became the foundation for further theorems, an increasingly large part of mathematics might depend on things that could be proved to exist, but never actually exhibited. The disagreement became especially sharp because different mathematicians had different ideas about the relationship between mathematics and human knowledge. One view treated mathematical objects as existing independently of us. According to this attitude, a mathematical structure does not need to be constructible by a human mind in order to be legitimate. If the axioms imply that an object exists, then our inability to describe it explicitly is our limitation, not the object's. Imagine an enormous landscape extending beyond everything you can see. The fact that you cannot visit every hill does not mean the hills disappear. A supporter of broad, non-constructive reasoning might think about mathematics in something like this way. Infinite sets and their members exist within the mathematical universe, and proofs allow us to establish truths about them, even when no person could inspect every object individually. A more constructive viewpoint puts greater emphasis on the methods available to us. To say that something exists should mean more than showing that its non-existence would be inconvenient or contradictory. Ideally, mathematics should provide a process that produces the object, or at least specifies it unambiguously. The difference may sound philosophical, but it changes what kinds of proofs are acceptable. Consider a very simple logical argument. Suppose you know that one of two possibilities must be true, but you have no method for deciding which. A classical mathematician can often proceed using the fact that one possibility or the other must hold. A more constructive mathematician may insist that without a procedure distinguishing them, the statement provides less information than it first appears to. The axiom of choice magnifies this tension because it concerns not one undecided possibility, but potentially an enormous collection of them. For each non-empty set, there is at least one possible choice. Classical reasoning is comfortable moving from all these individual possibilities to the existence of one complete selection. Constructive reasoning asks where that complete selection actually came from. This is why it would be misleading to describe the historical debate as one side loving infinity, and the other side being afraid of it. The critics were not necessarily rejecting all infinite mathematics. They were asking what kinds of reasoning involving infinity were justified. Some were comfortable with infinite sets when their elements could be generated according to explicit rules. A sequence whose members can be calculated one after another feels different from an arbitrary collection, whose members may have no usable description. The axiom of choice deliberately ignores that distinction. It applies even when the sets involved offer no selecting rule at all. This unrestricted nature made the axiom extraordinarily powerful, but it also made it a perfect target for foundational disagreement. One group of mathematicians could point to elegant theorems and say that choice allows mathematics to reveal deep structures that would otherwise remain inaccessible. Another could point to non-constructive sets and strange paradoxes and ask whether the same power was telling us something meaningful or simply revealing that our assumptions were too generous. The Banach-Tarski paradox became a particularly memorable example, but the deeper disagreement existed before it. The paradox simply gave the philosophical argument a very convenient sphere to stand on. If accepting choice allowed the construction of non-measurable sets and bizarre decompositions, critics could argue that the axiom was taking mathematics too far from ordinary notions of quantity. Supporters could respond that ordinary intuition had no authority over arbitrary infinite sets. A strange consequence was not a contradiction, and mathematics had encountered many correct results that initially seemed absurd. The same sort of disagreement had happened before. Negative numbers once appeared suspicious. Imaginary numbers seemed even worse. Non-Euclidean geometry challenged assumptions about space that had felt obvious for centuries. Each time, mathematics became larger by allowing concepts that initially seemed unnatural. Perhaps the axiom of choice was simply another step in that tradition. But there was an important difference. Negative numbers and imaginary numbers could be manipulated explicitly. You could calculate with them. The strange objects produced through unrestricted choice might have no explicit construction at all. This made the debate harder to settle through ordinary mathematical practice. The usefulness of choice continued to grow. Mathematicians discovered that it was connected to numerous important statements throughout different fields. In algebra, it could guarantee the existence of bases for very general vector spaces. In other areas, it supported the existence of maximal structures. It was equivalent to the well-ordering principle that had originally motivated Zermelo, and later formulations such as Zorn's lemma gave mathematicians a version of the same logical power that proved extremely convenient in everyday work. This created an interesting social change inside mathematics. A foundational principle that had once seemed controversial could appear in a proof without being announced dramatically. A mathematician might use Zorn's lemma because it fit the problem naturally, even though the lemma carries the strength of the axiom of choice. The controversy did not vanish, but practical mathematics had begun making its own decision. If a principle repeatedly solves useful problems, mathematicians tend to become comfortable with it, especially when no contradiction appears. The axiom of choice gradually became normal in much mainstream mathematics. That did not mean everyone suddenly agreed about its philosophical interpretation. It meant that the mathematical benefits were substantial enough that many researchers accepted the rule as part of their working foundation. There is something important here about the difference between asking whether an axiom feels obvious and asking whether a mathematical theory built with it is fruitful. Axioms do not have to resemble laws observed in nature. They are starting assumptions defining a formal framework. Once the assumptions are stated, mathematics investigates their consequences. From this perspective, the right question may not be whether the axiom of choice is intuitively true. The better questions might be whether it is consistent with the rest of the framework, what theorems it allows, and what happens when it is removed. This shift eventually changed the entire argument. For a while, people could still hope that the disagreement would be settled in the traditional way. Perhaps someone would prove choice from simpler accepted assumptions. Then the supporters would win, at least within that foundation. Or perhaps someone would derive a contradiction from choice. Then the critics would have a decisive mathematical reason to reject it. As we have already seen, neither outcome arrived. The work of Kurt Gödel showed that, assuming the ordinary axioms of set theory are themselves consistent, adding the axiom of choice does not create a contradiction. Later, Paul Cohen showed that those ordinary axioms cannot prove choice either. The principle was independent. This result completely altered the nature of the disagreement. Mathematicians could no longer treat the axiom merely as an unresolved theorem, waiting for a sufficiently clever proof. Within the usual foundational framework, no such proof was coming. Choice was genuinely additional. You could accept it. You could reject it. The remaining axioms would not make the decision for you. That realization transformed what had sounded like a fight over truth into an exploration of alternatives. Suppose you accept the axiom of choice. You obtain the mathematical universe most working mathematicians are familiar with. Every set can be well ordered. General vector spaces have bases. Powerful maximality principles are available. Many proofs become clean and elegant. Non-measurable sets exist, and consequences like Banach-Tarski are allowed. Suppose you do not accept the axiom. Mathematics does not collapse. Numbers do not disappear. Calculus does not wake up one morning and resign. Ordinary finite mathematics remains untouched, and large portions of analysis, algebra, geometry, and other fields continue functioning. What changes are certain very general claims about infinite collections. Some sets may no longer be guaranteed a well-ordering. Some selection processes can fail. Some objects whose existence was automatic with choice become uncertain or unavailable. Certain theorems require modification. This makes the decision far more interesting than choosing between mathematics and no mathematics. The real choice is between different versions of infinite mathematics. There are also positions between full acceptance and complete rejection. Mathematicians have studied weaker forms of choice that permit selections under more limited circumstances. Perhaps choice is allowed for collections that can themselves be listed in sequence. Perhaps only certain classes of sets are considered. These weaker principles can preserve many useful results without granting the full power of unrestricted choice. The subject becomes less like a simple argument and more like adjusting a control. How much choice does a theorem need? How much can be removed before the theorem fails? If a proof uses the full axiom, Is that genuinely necessary, or could a weaker assumption do the same work? These questions are now mathematical questions in their own right. There is something rather healthy about this outcome. The early controversy forced mathematicians to pay attention to hidden assumptions. Instead of casually writing "choose one from each set," they learned that such a phrase might contain real logical strength. Proofs became more transparent because researchers could identify exactly where choice entered. That habit extends far beyond this particular axiom. Modern mathematics often asks not only whether a theorem is true under some broad collection of assumptions, but exactly which assumptions are needed. A result that requires less is often stronger. If you can prove something without the axiom of choice, you have learned that the theorem survives in a wider range of mathematical universes. If choice is essential, that is also meaningful information. In this sense, the fight over the axiom made mathematics more self-aware. It showed that a proof is not merely a chain of conclusions. It is a chain resting on a particular foundation, and different foundations can support different landscapes. The philosophical disagreement also survives in modern forms. Constructive mathematics remains an active approach, and mathematicians continue studying systems where existence is tied more closely to explicit methods. Classical mathematics, meanwhile, generally accepts principles that constructive approaches may avoid. These are not simply rival camps shouting across a hallway. They are different ways of investigating what follows when the rules of reasoning are adjusted. A theorem proved constructively often contains additional practical information because the proof explains how to obtain the object involved. A classical non-constructive proof may be shorter or apply in much greater generality. Both can reveal something valuable. The axiom of choice sits almost perfectly at the boundary between those attitudes because it offers enormous generality while asking for very little constructive information. It says that the selected objects are there. It does not promise to introduce you to them. Most working mathematicians have decided that this is acceptable. They use the axiom or statements equivalent to it when needed. The unusual consequences are treated as features of infinite set theory, rather than evidence that the system is defective. But that practical acceptance should not make the original controversy seem foolish. The critics identified something genuinely important. The axiom does change the kind of mathematical objects we are allowed to discuss. It does permit existence without explicit construction. It does have consequences that can challenge ordinary intuition. The supporters were also identifying something genuinely important. Refusing choice imposes restrictions that can feel artificial, and many powerful structures arise naturally once the axiom is accepted. Neither observation disappears simply because one convention became dominant. This is why calling the axiom controversial can be slightly misleading today if it creates the impression that mathematicians are constantly arguing about whether to remove it from textbooks. In mainstream mathematics, full choice is widely accepted as part of the usual foundational setting. The historical controversy matters because it exposed choices inside mathematics that had previously been invisible. It revealed that even a subject famous for certainty has places where we must decide which rules we want to investigate. Once the rules are selected, the proofs can be completely rigorous. The flexibility comes before the proof begins. That may sound unsettling if we imagine mathematics as a single enormous building whose foundations were fixed long before anyone arrived. A better picture is that mathematics contains several carefully constructed buildings. Some share most of their foundations, but differ in a few structural assumptions. Inside one building, the axiom of choice is available. Inside another, it is not. The rooms can look surprisingly similar at first. Ordinary arithmetic works. Familiar finite sets behave normally. Much of everyday mathematics continues exactly as expected. Only when you travel far enough into infinite collections do the differences become obvious. This raises a question that is far more interesting than simply asking who won the historical argument. What is it actually like to do mathematics in a universe where the axiom of choice fails? We have spent a great deal of time looking at what choice permits, but removing it is not merely a philosophical gesture. It produces mathematical worlds with genuinely different properties. Some collections that would automatically have selectors in ordinary set theory may have none. Some infinite sets can behave in ways that seem unusual to mathematicians accustomed to choice. The relationships between different notions of size can become less orderly. Statements that usually appear together can separate. There are even mathematical models where every set of real numbers behaves much more nicely with respect to measurement than it does when unrestricted choice is available, although obtaining such worlds requires careful attention to which other assumptions are being used. That creates a fascinating reversal. We have seen the axiom of choice produce strange objects such as non-measurable sets. Without full choice, some of those troublesome objects may disappear and the mathematical continuum can become better behaved in certain respects. But the price is that other familiar structures disappear with them. The question then becomes less about whether choice is good or bad, and more about what kind of infinite universe we want to explore. Removing the axiom does not restore common sense in every possible way. It trades one collection of properties for another, and this is where the argument becomes a genuine journey into alternative mathematics, because there are coherent worlds in which the selections we have been casually granting for most of this discussion simply cannot be guaranteed. To understand what that means, we need to enter one of those worlds and see what changes when mathematics is no longer allowed to say, whenever it wishes, that one object can be chosen from every non-empty collection. Once you know that the axiom of choice cannot be forced upon mathematics by the other usual rules of set theory, a very natural question appears. What happens if we simply do not accept it? This sounds at first like removing one optional tool from a large mathematical toolbox. Perhaps a few proofs become longer, a few convenient theorems need replacing, and otherwise mathematics continues much as before. For ordinary finite problems, that picture is surprisingly close to the truth. Addition still works. Geometry does not suddenly forget what a triangle is. Calculus does not become offended and leave the building. The interesting differences begin when we return to the infinite world where choice was doing most of its work. There is one important point to keep clear before entering this world. There is not one single universe called mathematics without the axiom of choice, in which every unusual phenomenon happens at once. There are many possible mathematical models in which the usual rules of set theory hold, while the full axiom of choice fails. Different models can behave differently. One may contain a particularly strange infinite set, while another does not. One may make collections of real numbers remarkably regular, while another produces a different kind of irregularity. Removing choice opens a landscape of possibilities rather than replacing one rigid mathematical universe with another. The easiest way to feel the difference is to return to the idea of ordering. With the axiom of choice, every set can be well ordered. Even if the members of a set have no natural first element and no obvious arrangement, some well ordering exists. This does not mean that anyone can necessarily write the ordering down, but mathematics is allowed to assert that it is there. Once full choice is unavailable, that guarantee disappears. There can be sets for which no well-ordering can be established inside the mathematical universe being considered. The objects have not vanished, but the permission to place them into that extremely convenient form of order has vanished. This changes the way we think about size. Under full choice, any two sets can be compared in cardinality. One is no larger than the other, or the other is no larger than the first, or they have exactly the same size. Infinite sizes form a beautifully ordered hierarchy. Without the axiom of choice, this tidy comparison can fail. There can be cardinalities that are not comparable in the usual way. Neither set can be injected into the other in the manner needed to declare one at least as large as the other. Work in set theory without choice shows that the familiar universal comparability of cardinal numbers depends on choice, and does not survive automatically once the axiom is removed. This is already rather strange because our ordinary understanding of size assumes that comparison should always be possible. If I place two piles of books on the floor, either the first pile contains more books, the second does, or the piles contain the same number. With finite collections, nothing dramatic happens. Even if the piles are enormous, the principle remains clear. Infinite sets without choice can refuse to line up so politely. Asking which of two infinite collections is larger may no longer receive one of the answers our finite intuition expects. There is an even more surprising possibility. Without choice, an infinite set can behave in a way that seems almost finite. In ordinary mathematics with the axiom of choice, an infinite set contains a countably infinite subset. If you know the set is genuinely infinite, you can keep extracting distinct members and arrange at least some of them in an endless sequence. That fact is so familiar that it barely looks like a theorem. Without choice, however, models can contain infinite sets from which no countably infinite sequence of distinct elements can be selected. Such objects are often called Dedekind finite sets. They are infinite because they cannot be matched with any finite collection, yet they do not behave like the infinite sets we usually meet in elementary mathematics. One modern construction shows that there are models of set theory without any form of choice, containing an infinite Dedekind finite set of real numbers. In the same setting, familiar assumptions such as the statement that a countable union of countable sets must itself be countable are not automatically available. Try to imagine what that means without turning it into a physical picture too quickly. You have an infinite collection, so there is no finite number that counts all of its members. Yet you cannot select a first member, then another distinct member, then another, continuing forever in the familiar way. The set is endless in one sense, but refuses to supply the kind of endless list our minds normally associate with infinity. This sounds almost contradictory because we have been trained to think that infinite means there must always be another object available. If there is always another one, surely we should be able to keep choosing. But that final word is exactly where the axiom has been hiding. To produce an infinite sequence of distinct objects, you repeatedly need to select a new object from what remains. When a sufficiently strong choice principle is available, this causes no difficulty. Without it, saying that every stage has another possible object does not automatically provide one completed, infinite sequence of selections. The same issue appears in the innocent-sounding statement that a countable collection of countable sets should have a countable union. Suppose you have a sequence of boxes. Every box contains a countable collection of objects. Surely if there are only countably many boxes and each contains only countably many objects, combining everything should still produce a countable set. In the mathematical world most of us learn, this result feels completely routine. Yet proving it in full generality requires a certain amount of choice. You need compatible enumerations of the individual collections so that their members can be brought together into one master list. Without an appropriate choice principle, models can behave differently. Set theorists therefore distinguish between the full axiom of choice and weaker principles that allow choice only in more restricted situations. This is not philosophical decoration. It changes which familiar operations with infinite collections can be justified. This gives us a useful way to picture mathematics without full choice. It is not a world where nobody can ever choose anything. That would be rather difficult to work with and would make ordering lunch unnecessarily foundational. Many selections can still be made. If a collection has an explicit rule, use the rule. If every set has a clearly distinguished member, select that member. If the sets are finite under suitable circumstances, many choices can be handled directly. What disappears is the universal promise that arbitrary selections always exist regardless of structure. There are also weaker choice principles that preserve much of ordinary mathematical reasoning. One particularly important example allows sequences of choices where each new selection may depend on the selections already made. This is strong enough for a great deal of analysis and other familiar mathematics, yet weaker than the full axiom of choice. The existence of such intermediate principles is one reason the subject becomes much richer than simply declaring choice, either present or absent. Instead of asking whether we have choice, mathematicians can ask how much choice we have. This distinction becomes especially interesting when we return to measurement. Earlier, the Banach-Tarski paradox required extraordinarily irregular sets that could not be assigned ordinary volume. Similar non-measurable collections also appear on the real number line when strong forms of choice are available. A natural thought is that perhaps a mathematical universe without full choice could prevent at least some of these troublesome sets from existing. Robert Solovay demonstrated a remarkable version of exactly that possibility. In 1970, he published a construction of a model of set theory in which every set of real numbers is Lebesgue measurable. Lebesgue measure is the mathematical framework that extends the ordinary idea of length to extremely general collections of points. Under the usual set theory with full choice, there are subsets of the real line to which this ordinary notion of measure cannot consistently be assigned. Solovay showed that one can instead obtain a mathematical universe in which every set of reals behaves well enough to be measurable, provided suitable additional set theoretic strength is assumed in the background of the construction. That is an extraordinary reversal. With strong choice, mathematics gains the power to select representatives so freely that highly irregular non-measurable sets become available. In the kind of universe Solovay studied, full choice is absent and the real line becomes, in an important sense, much better behaved. Every subset can be assigned the sort of measure that ordinary analysis would like to have. If Banach-Tarski made you feel that the axiom of choice allows mathematics to become slightly unruly, this alternative universe may sound pleasantly civilized. Every set of real numbers measurable. No need to worry about mysterious selections creating collections that escape the usual notion of length. Perhaps we should simply move into this universe, unpack the mathematical furniture, and never speak of unrestricted choice again. Unfortunately, mathematics rarely allows a foundational decision to be made entirely on the basis of which universe has the tidiest living room. Giving up full choice removes useful structures as well as troublesome ones. The same principle that helps create non-measurable sets also proves major existence theorems throughout algebra, analysis, topology, and other areas. Without it, statements that are effortless in the usual framework may require extra hypotheses or may simply fail in full generality. Every vector space having a basis, every set being well orderable, and broad maximality principles are all connected to the same choice machinery. This makes the situation more subtle than saying choice creates pathological objects, while rejecting choice makes mathematics nicer. Sometimes choice is exactly what makes mathematics orderly. It compares arbitrary cardinalities, it gives well orderings, it produces maximal objects, it guarantees bases. In other situations, the enormous freedom it grants allows objects so irregular that familiar notions of measurement break down. Choice creates order and disorder at the same time, depending on what you're examining. That apparent contradiction comes from the unusual nature of the principle. It does not tell the selected objects to be regular, it merely guarantees that selections exist. The resulting global structure may be extremely useful, as with a basis or well-ordering. But the particular selections themselves can also be so arbitrary that they generate wild subsets with no natural geometric description. A universe without full choice removes some of that freedom. The price is that it also removes some of the structures that freedom was capable of producing. The strange infinite sets found in models without choice make this trade especially visible. Consider again an infinite Dedekind finite set. Under full choice, an infinite set behaves generously. At minimum, you can find a countably infinite collection of distinct members inside it. Remove the relevant selection principle, and infinity can become reluctant. The set contains more than any finite number of objects, yet it does not hand you an ordinary infinite sequence. There are even stronger examples studied in set theory without choice, such as amorphous sets. An amorphous set is infinite but cannot be divided into two disjoint, infinite subsets. Every subset is either finite or has a finite complement. Such objects cannot exist when full choice is available, but they can appear in suitable models without it. The idea is profoundly different from the infinity we usually meet. where splitting an infinite collection into two infinite pieces seems almost automatic. Think of the positive whole numbers. Separate the even numbers from the odd numbers, and you immediately have two infinite collections. That operation feels so basic that we may unconsciously treat it as a defining feature of infinity. An amorphous set shows that without choice, the concept of infinity can separate from this familiar behavior. Being infinite only tells you that the set is not finite. It does not automatically grant every property we have learned to associate with endless sequences. This is one of the deepest lessons that comes from studying mathematics without the axiom of choice. Many statements that feel like facts about infinity turn out to be facts about infinity together with choice. We usually learn them in a mathematical environment where the axiom is already present, so the distinction remains invisible. Every infinite set contains a countably infinite subset. Every pair of cardinalities can be compared. Every set can be well ordered. Countable unions of countable sets behave as expected. These statements begin to look like part of the natural meaning of infinity itself. Remove choice, and some of them separate. Mathematicians can then examine exactly which form of choice is responsible for which conclusion. This is one reason set theory without choice remains valuable, even for researchers who are perfectly happy using the axiom in their everyday mathematics. It reveals dependencies that would otherwise remain hidden. It is a little like removing electricity from a house, one circuit at a time, to discover which light switches were secretly connected to the same wire. As long as everything works, you may never notice the underlying relationships. Once a circuit is removed, the architecture becomes visible. The fact that multiple models exist also prevents us from making overly simple statements about what happens when choice is false. One model may contain infinite Dedekind finite sets. Another may satisfy stronger weaker choice principles that rule out certain examples. One may have unusually regular sets of real numbers. Different failures of choice can be carefully engineered to investigate different questions. Research in this area is not about discovering one bizarre opposite of standard mathematics. It is about mapping many possible combinations of properties. This is where the word universe becomes useful, provided we do not take it too literally. Set theorists often speak about models as different mathematical universes because each contains objects and relationships satisfying a particular collection of axioms. From within one model, a certain set may exist and a certain theorem may hold. In another, the relevant object may be absent or the theorem may fail. Nobody is suggesting that there is a telescope somewhere capable of observing these universes. They are logical structures. Still, the language captures an important feature. Once an axiom is independent, the remaining rules permit more than one coherent mathematical world. That can be surprising because mathematics is often presented as the place where every properly asked question has exactly one answer. Many ordinary questions do. Once you fix the rules, the consequences can be rigid and unavoidable. Independence reveals that sometimes the rules themselves do not settle the statement under discussion. The axiom of choice provides one of the clearest examples. Inside a mathematical universe with full choice, asking whether every set can be well ordered has an immediate answer: yes. Inside a model where choice fails, the answer can be no. Neither response results from sloppy reasoning. The two universes begin with different foundational commitments. What makes this especially interesting is how ordinary both universes can look near the surface. If all you do is arithmetic with everyday numbers, you may never notice the difference. Finite calculations continue as expected. Basic geometry continues as expected. Much of standard analysis can be carried out using principles weaker than full choice. You have to travel far enough into infinite collections before the landscape begins to change. Then the differences can become dramatic. An infinite set that contains no countably infinite subset. Cardinalities that resist comparison. Collections whose unions behave unexpectedly. Sets of real numbers that are all measurable in a universe where the non-measurable examples, familiar from full choice, are unavailable. These are not errors introduced by removing an obviously necessary axiom. They are demonstrations that some of our most familiar beliefs about infinity were never consequences of logic alone. Choice was helping. Once you see this, the historical argument between supporters and critics becomes much easier to understand. The supporters were not simply defending a convenient shortcut. They were defending a principle that makes the infinite world highly structured and supports powerful existence results. The critics were not merely objecting because some conclusion seemed strange. They were questioning whether mathematics should automatically include objects and selections that no explicit procedure could produce. Modern set theory has enough room to study both attitudes. A mathematician can work comfortably in the usual framework with the axiom of choice and take advantage of its enormous power. Another investigation can deliberately remove the axiom or replace it with weaker forms to see which theorems survive. Neither activity requires pretending the other framework does not exist. That may be one of the most interesting outcomes of the entire controversy. The discovery that choice is independent did not force mathematics to select a permanent winner. It turned the disagreement itself into something mathematics could study. We can ask what follows with choice. We can ask what follows without it. We can ask which weaker principles are enough for particular theorems. We can compare the resulting universes and learn which parts of familiar mathematics depend on assumptions we might otherwise never notice. And after wandering through these alternatives, the question that remains is no longer simply whether the axiom of choice is true. That phrasing begins to feel too small. The more useful question is what kind of mathematics we obtain when we accept it, what kind we obtain when we do not, and whether the enormous power it gives us is worth the strange objects that come along with it. That is where the final decision becomes less like settling a technical dispute and more like deciding what we want the foundations of mathematics to permit. After everything we have seen, the question now sounds much less innocent than it did at the beginning. Should mathematics accept the axiom of choice? If we had asked this before wandering through infinite collections, non-constructive existence, well-ordering, different sizes of infinity, and a sphere that can be decomposed in a way that appears to produce two copies of itself, the answer might have seemed easy. If every collection contains at least one object, surely choosing one from each should be harmless. But the entire story of the axiom of choice is really the story of discovering how much can hide inside a sentence that sounds obvious. The first thing worth noticing is that mathematics does not need one emotional response to the axiom. It does not need to declare the principle beautiful, dangerous, sensible, absurd, or morally questionable before using it. Mathematics can ask a more practical question. What happens if we accept it, and what happens if we do not? That change in perspective is one of the most useful outcomes of the entire controversy. If we accept the axiom of choice, a great deal of infinite mathematics becomes wonderfully organized. Every set can be well ordered. Very general vector spaces have bases. Powerful maximality arguments become available. Many proofs that would otherwise require awkward additional conditions can proceed cleanly. Mathematicians can select representatives from arbitrary collections and use those selections to build larger structures. This is enormously convenient, but convenience is not the only reason choice is attractive. The axiom also fits naturally with a broad classical view of mathematical existence. According to that view, a mathematical object does not need to be explicitly constructed in order to exist. If the logical assumptions guarantee that something exists, that is enough. This attitude is already familiar in mathematics. There are proofs showing that certain objects must exist, even when the proof does not provide a direct recipe for finding them. There are theorems where contradiction eliminates every alternative and leaves existence as the only possibility. Mathematicians use such reasoning constantly. Choice extends that willingness into very large collections. If every set in a family contains at least one object, then a complete selection exists. We may not know the selections individually. We may never be able to describe them. Still, within the mathematical universe created by those axioms, they are available. For many mathematicians, this is perfectly reasonable. mathematics is not limited by the speed of a computer, the lifespan of a human being, or the number of symbols anyone can physically write down. If the subject studies infinite structures, then perhaps we should expect some objects to exist beyond anything we can explicitly list. A star can exist without anyone visiting it, and a mathematical object can exist without anyone constructing every part of it. Of course, the comparison is not exact. Mathematical objects and physical stars are very different things, but the intuition behind the position is understandable. Human accessibility does not have to be the boundary of mathematical existence. This is one reason full choice became standard across much of mainstream mathematics. It produces a powerful and elegant framework, and mathematicians have learned how to work comfortably with the strange consequences that come with it. Banach-Tarski no longer represents a crisis, it represents a warning about intuition. The theorem tells us that arbitrary infinite point sets do not behave like pieces of physical material. It does not tell us that mathematics is inconsistent. Once the distinction is understood, the paradox becomes less of a threat, and more of a demonstration of how far abstract sets can depart from ordinary geometry. The same is true of non-measurable sets. The fact that not every collection of points can be assigned an ordinary length or volume does not destroy measurement. It tells us that the notion of measure has a domain where it behaves properly, and that unrestricted set formation can create objects outside that domain. Mathematics has many ideas like this. A function may fail to be continuous, a shape may fail to have a smooth boundary, a collection may fail to have ordinary measure. The existence of unusual objects does not invalidate the well-behaved ones. From this point of view, refusing the axiom simply because some consequences are strange would be a little like refusing complex numbers because they do not behave like ordinary distances on a number line. Strangeness alone is not a mathematical argument, but there is another side, and it deserves more than a polite mention. The axiom of choice really does allow mathematics to assert the existence of objects that no procedure can identify. It really does separate the statement that something exists from the ability to construct it. If you believe that mathematical existence should carry computational or constructive meaning, this can be deeply unsatisfying. Imagine being told that somewhere in an enormous library there is a book satisfying exactly the property you need. You ask for the title, and no one can give it to you. You ask where it is located, and no one can tell you. You ask whether there is a procedure for finding it, and the answer is no. The only information available is that logic guarantees that the book must exist. In classical mathematics, this can be enough. In constructive mathematics, it may not be. A constructive approach often asks for additional information. If you claim that an object exists, show how it can be produced. If you claim that a choice can be made, provide the choice or a method that determines it. This is not merely stubbornness. Constructive proofs can offer something extremely valuable. They frequently give algorithms explicit examples or procedures that can actually be carried out. When the proof is finished, you know more than the bare fact that an object exists. There is therefore a genuine trade-off. Classical reasoning with choice often gives greater generality. Constructive reasoning often gives greater explicitness. Neither goal is automatically superior in every situation. If you are proving a broad theorem about abstract structures, general existence may be exactly what you want. If you are designing an algorithm, calculating an approximation, or trying to produce a usable object, a proof that merely says something exists somewhere may be considerably less helpful. This is why mathematics does not need to turn the question into a permanent vote. A mathematician can accept the axiom of choice in one foundational setting and still care deeply about finding constructive proofs whenever possible. Using choice does not require celebrating non-constructive reasoning on every occasion. Likewise, studying mathematics without full choice does not require denying the value of classical mathematics. Different frameworks answer different questions. This becomes clearer when we remember the independence results. The ordinary axioms of set theory do not prove the axiom of choice, and they do not disprove it, assuming the foundational system is consistent. That means the usual rules do not settle the matter for us. There is no hidden theorem waiting to announce that choice was secretly mandatory all along. There is also no hidden contradiction waiting to show that generations of mathematicians made a terrible mistake. The independence of choice changes the meaning of the original question. Asking whether mathematics should accept the axiom is not quite like asking whether a particular calculation is correct. It is closer to asking which mathematical framework is most useful for the kind of investigation we want to conduct. With choice, one landscape appears. Without it, another appears. With weaker forms of choice, still others appear. Once we understand this, the word should become less absolute. Should a geometer use Euclidean assumptions when studying ordinary flat geometry? Certainly. Should a geometer therefore refuse to study curved geometries? Of course not. The existence of alternative systems does not make one useless. It gives mathematics more structures to explore. The axiom of choice can be approached in a similar way. For much mainstream mathematics, accepting it is extremely convenient and has become standard practice. It supports a large body of familiar theory and allows broad theorems to be stated cleanly. For foundational investigations, however, refusing it can be equally informative. Removing choice reveals exactly where mathematics depended on it. An infinite set may no longer contain a countably infinite subset. Certain cardinalities may become impossible to compare. Some sets of real numbers may behave more regularly with respect to measurement. The mathematical universe changes in ways that teach us which properties came from infinity itself, and which came from infinity combined with choice. That distinction is easy to miss when we live entirely inside one framework. If every theorem you learn uses the same foundational assumptions, those assumptions can begin to feel like laws of nature. Set theory reminds us that they are assumptions, very powerful ones, carefully studied ones, enormously successful ones, but assumptions nevertheless. There is something rather pleasant about the fact that the axiom of choice makes this lesson so difficult to avoid. Its name almost sounds as though mathematics is teasing us. We began with the question of choosing one object from each collection, and we ended with mathematics itself facing a choice about whether that principle should be part of the foundation. If we accept it, we gain an extraordinary amount of structure. If we reject it, we gain the ability to explore mathematical worlds, where some familiar structures disappear and other forms of regularity emerge. There is no requirement that one of these worlds be declared fake. What matters is stating clearly which assumptions are being used. This is one of the quiet strengths of mathematics. Once the rules are specified, disagreement can become precise. Instead of one mathematician saying that a theorem feels reasonable and another saying that it feels suspicious, they can ask whether the theorem follows from a particular collection of axioms. If it does, there is a proof. If it does not, perhaps another assumption is required. If it is independent, that fact itself becomes a theorem. Even disagreement can be studied mathematically. That may be the most interesting part of the story. The early arguments about choice were intense, because mathematicians were trying to determine what counted as legitimate reasoning. They were not yet looking at a fully mapped landscape of alternative models. They were standing much closer to the foundations while those foundations were still being built. Today, we have the advantage of knowing that the axiom can be added consistently relative to the usual set theory, and that it can also fail in suitable models. This allows us to view the old controversy with less urgency. We do not have to decide that one side was foolish. The supporters recognize that choice unlocks powerful mathematics. The critics recognize that it introduces genuinely non-constructive objects and assumptions that should not be treated as invisible. Both observations survived. Mainstream practice largely chose the powerful route, but foundational research kept the alternatives alive. That is probably the most balanced answer to the question. Should mathematics accept the axiom of choice? For the broad classical framework used throughout much of modern mathematics, accepting it is extremely useful and entirely standard. Should every possible form of mathematics be required to accept it? No. Studying what happens without it has taught us far too much. The value of the axiom does not come from forcing every mathematician into one universe. It comes partly from the contrast between the universes where it holds and those where it does not. Once you see both, the principle becomes more than a rule. It becomes a way of understanding the architecture of mathematical reasoning. Think back to the very first boxes we imagined. Each box contained at least one object. At the beginning, the instruction to take one from each seemed almost too simple to discuss. Then the boxes became infinite. The labels disappeared. The ordering disappeared. The rule for selecting disappeared. We discovered that there might be no ordinary process for making the selections, yet one axiom could guarantee that a completed selection existed anyway. From that modest permission came well orderings, maximal structures, bases, non-measurable sets, and one of the most famous paradoxes in mathematics. Then we removed the permission and discovered another strange world, one containing infinite sets that might not hold ordinary infinite sequences and sizes that might resist comparison. Neither side restored the simple intuition we had at the beginning. That may be the clearest lesson of all. Infinity does not become completely comfortable, whether we accept choice or reject it. The axiom is not the source of everything strange about infinity. It is one particular way of organizing that strangeness. With choice, infinite mathematics gains an enormous amount of structure, but that structure can support wildly non-constructive objects. Without choice, some pathological objects disappear, but familiar forms of organization disappear as well. There is no version where infinity simply behaves like a very large finite collection. It was never going to. Our minds want infinity to be ordinary arithmetic that happens to continue for a very long time. Set theory keeps reminding us that actual mathematical infinity is something different. It can contain a proper part as large as the whole. It can come in different sizes. Its sizes may depend on foundational principles for their comparability. Its members may resist being arranged into sequences, and with sufficient choice, its points can be organized into sets that make a single ball appear capable of becoming two. The axiom of choice is controversial, not because mathematicians failed to understand these consequences. It is controversial because they understood them very well. They saw that a tiny-looking assumption changed the behavior of the infinite world in profound ways. Perhaps that is why the axiom remains such a beautiful example of foundational mathematics. You do not need an enormous collection of technical machinery to state the basic idea. A child can understand the instruction to choose one object from each box. The difficulty arrives only when we ask whether that simple intuition should survive every possible infinite situation. Mathematics answers that it can if we choose an axiom that allows it, and after everything that follows from that decision, perhaps the most surprising fact is not Banach-Tarski or non-measurable sets or incomparable infinities. Perhaps it is that mathematics can remain rigorous even when more than one foundational path is available. Certainty does not require having only one starting point. It requires being clear about where you started and following the consequences carefully. That is a useful thought far beyond set theory. We often imagine mathematics as a finished collection of unquestionable facts, but its deeper foundations are full of decisions about definitions, axioms, and the structures we want to investigate. The remarkable achievement is not that mathematicians avoided making choices, it is that they learned how to make those choices explicit. The axiom of choice may therefore deserve its controversial reputation, but perhaps not for the reason people first expect. The most important thing about it is not that it allows a mathematical sphere to behave strangely. It is that it forces us to notice what we mean when we say something exists. Does existence require a construction? Is logical necessity enough? Should every infinite collection be organized as strongly as possible? How much are we willing to assume in exchange for generality? Those questions do not disappear when the theorem is proved. They sit underneath the proof. And here, after travelling from ordinary selections to some of the strangest corners of infinity, we return to the same small act that began everything. You have several possibilities in front of you, and you decide what you're willing to choose. Mathematics, perhaps appropriately, does exactly the same.